During the Silurian period, Earth is a planet in recovery. Seas spread wide across low continents, coral reefs begin to flourish again, and strange armoured fish patrol warm shallow waters. The climate settles after earlier upheavals, ice retreats and coastlines shift as land slowly rises and sinks. Along the edges of these ancient shores, the first small plants take hold, hinting at a future where life will move onto land for good. If you enjoy quiet journeys into deep time, please like, subscribe and share. Thank you for watching. Now let's begin. Seen from far above, the Silurian Earth presents a surface dominated by water. Most of the globe is covered by a single connected ocean, a vast panthalassic expanse that wraps almost entirely around the planet. The few large land masses are clustered mainly in the southern half of the world, with one great continent, Gondwana, spread across high southern latitudes. Its outline is irregular, with broad bulging promontories and embayments, where shallow seas lap far into the interior. Parts of Gondwana still carry traces of the earlier cold interval, and in the early Silurian, some regions near the South Polar Zone hold lingering ice sheets and mountain glaciers. These pale areas blend with cloud decks in the polar atmosphere, but the underlying shape of the continent remains clear as a dark, rough surface where rock and thin soils show through. As time moves forward within the period, the ice shrinks, and the bright streaks of permanent snow retreat toward the pole, leaving more of the continent ice-free. North of Gondwana, across the equatorial and northern belts, smaller continents and microcontinents drift in the surrounding ocean. Laurentia, the core of what will one day include much of North America and Greenland, sits near the equator and sometimes straddles low northern latitudes. From orbit, it appears as a mostly low-lying region, with large areas of its margins drowned under warm, shallow seas. Only central blocks stand clearly above sea level, forming a patchwork of islands and peninsulas. To the northeast lies Baltica, another relatively small continent that has migrated from higher southern latitudes toward a position closer to the equator. Its edges too are trimmed by flooded shelves, turning it into an irregular shape, with tongues of seawater cutting inland. Farther away, Siberia occupies a more isolated position, separated by broad stretches of ocean. Its outline is harder to fix in a single snapshot, because of the constant reshaping by rising and falling seas and by slow tectonic uplift and subsidence. But it forms yet another piece of a broken northern archipelago, scattered over wide tropical and subtropical waters. Where oceans encroach on continents, the colour seen from orbit changes in a smooth gradation from deep blue to paler turquoise. The deepest parts of the panthalassic interior appear as dark, almost uniform blue patches, broken only by the white curls and streaks of cloud systems passing overhead. Closer to the continents, light reflects from the seafloor in shallower zones, giving flooded shelves a lighter hue. Extensive epicontinental seas, which are shallow bodies of marine water, spread across once dry continental crust, appear as broad, glowing regions slightly greener or more turbid, especially where rivers deliver fine sediments from the interior. During much of the Silurian, global sea level stands high, so these flooded regions are widespread. From space, this makes the true outlines of the continents less sharply defined than in later eras, since large parts of their margins lie under several tens of meters of water, rather than in clear view as dry land. The absence of large land plants means that the colour and texture of the continents is also different from modern expectations. There are no extensive dark green belts of forests, no wide grasslands, and no deep networks of wetlands with dense foliage. Instead, much of the exposed land appears in muted tones of grey-brown and dull reddish hues, reflecting bare rock, weathered regolith, and thin, patchy coverings of early plants and fungi. Along coastlines and near river mouths, small clusters of low vegetation may begin to give a faint hint of green, but from the height of orbit these patches are subtle and easily lost in the broader pattern. The largest visually striking structures on land are long mountain belts and uplifted regions linked to ongoing collisions among the northern continents, where Laurentia and Baltica, along with other fragments, begin to interact a zone of deformation and early mountain building known to later geologists as part of the Caledonian-style orogeny rises. From above, this area appears as a sinuous band of elevated terrain casting longer shadows at low sun angles and tracing an arc that cuts across parts of the northern hemisphere. These mountains are not yet as high as later ranges like the Himalayas, but they stand above the surrounding lowlands enough to form a clear structural spine. Snow may seasonally coat their upper slopes, and erosion already starts to carve valleys that feed sediment into the adjacent seas. Cloud cover moves across this planet in broad, slowly shifting sheets and spirals. Large storm systems swirl over the Panthalastic Ocean, their bright cloud tops marking the centres of low-pressure zones. Over warm, shallow seas and near equatorial belts, broken fields of convective clouds show where moist air rises and cools. Over the interiors of Gondwana and the smaller northern continents, clouds are patchier, especially in dry regions far from the coasts. From the vantage point in space, these cloud patterns partially veil the surface, but careful observation over time makes clear that persistent blue dominates the low and middle latitudes, while brighter, more reflective regions cluster near remaining ice and frequent storm tracks. As the Silurian progresses, the gradual retreat of high-latitude ice on Gondwana changes the reflectivity of the southern polar area. Early in the period, white ice sheets and seasonal snowfields bounce a significant fraction of incoming sunlight back into space. Later, as warming continues and ice disappears from more sectors, darker rock and water occupy increasing areas. This shift can be recognized from orbit as a slow, darkening and smoothing of the polar cap with more open water and less permanent ice. The change affects how much energy the planet absorbs, but at this level of description it appears simply as a visual transformation of the southern high latitudes from a bright, patchy reflective surface to a more mottled mix of rock, soil and sea. River systems are harder to see directly from great heights, but their influence is visible where they meet the seas. At the edges of continents, fine sediments delivered by streams and deltas tint nearshore waters into subtle plumes that spread along the coasts. In some areas, these plumes outline the shape of drowned valleys and inlets, hinting at the underlying relief of the continental margins. Because there are no large rooted trees to stabilize soils, erosion on slopes and along channels can be efficient, sending pulses of mud and sand out into the shallow, epicontinental seas. Over time, this material settles and begins to build new layers on flooded shelves, but at the instant view from orbit it appears mainly as slight shifts in colour and opacity in the coastal waters. Life itself does not leave bold marks on this planet's face when seen from such a distance. The most diverse ecosystems are in the oceans, in reefs and on continental shelves, but they are too small to change the broad surface colours in a dramatic way. There are no glowing belts of city lights, no organised lines or patterns made by large land organisms. The only clear indicators that Earth is inhabited are the subtle greenish tints in some shallow seas, where phytoplankton and other microscopic organisms affect the way light is scattered, and the faint hints of low vegetation and fungi near coasts and river margins on land. These signs are present, but they do not dominate the image. Instead, the enduring impression of the Silurian Earth, when seen from space, is of a water planet with a few continents gathered in the south and scattered toward the north high seas that drown many of their edges, lingering but shrinking southern ice, and a dynamic skin of clouds that constantly redraws the details of the view while leaving the large-scale arrangement of ocean and land intact. The Silurian atmosphere forms a thin but crucial shell around the planet, a mixture of gases that controls how sunlight is filtered, how heat is stored, and how life in the oceans experiences its surroundings. Most of this air is still made of nitrogen, an element that does not easily take part in chemical reactions under normal conditions. Oxygen, the gas that many later animals rely on for breathing, is already present, but at levels lower than in later eras. Estimates from rock chemistry and fossil indicators suggest that oxygen makes up on the order of a little more than a tenth to perhaps a fifth of the atmosphere by volume, rather than the larger share found in more recent times. Carbon dioxide, the gas that traps heat and plays a central role in the greenhouse effect, is present at higher levels than in the modern atmosphere, likely many times higher, though exact values change through the period and remain uncertain. These three main gases, together with small amounts of others such as argon water vapour and trace sulphur and nitrogen compounds, form a layered system that stretches from the surface to the edge of space. Seen in cross-section, the Silurian atmosphere can be divided into broad, vertical zones, defined by how temperature changes with height. Closest to the ground and the sea surface lies the lowest layer where most weather occurs. In this region, often called the troposphere, temperature generally decreases with height, as warm air near the surface rises and cools. Cloud storms and day-to-day variations in wind and moisture occupy this part of the air column. The height of this active layer varies with latitude and with underlying surface conditions rising higher over warm tropical seas and lower over cooler high-latitude waters and land. Above it, a more stable region forms where temperature may remain steady or increase with height due to the absorption of ultraviolet light by certain gases, including ozone, which is a form of oxygen made of 3 atoms rather than 2. This zone, similar in its basic role to the later stratosphere, helps shield the surface and upper ocean from the most energetic solar radiation. Beyond that lie still higher and thinner regions where individual molecules are widely spaced, and where interactions with the solar wind and the planet's magnetic field become more important than ordinary weather. The amount of oxygen in the Silurian atmosphere is high enough to support active animal life in the oceans and in shallow waters and tidal zones, yet it is not so high that fires can spread as easily across any dry organic matter that might be present on land. In fact, with only low and patchy vegetation and fungi on land, and with moist conditions in the areas where they grow, there is little fuel for large natural fires. The oxygen level is also important for the chemistry of the oceans, because it helps control how deeply oxygenated waters can extend, and how much of the seafloor experiences low oxygen or nearly oxygen-free conditions. When air with a given oxygen content mixes with surface seawater, it sets the starting point for how much dissolved oxygen can be carried into deeper layers by circulation and mixing. Thus, the partial pressure of oxygen in the air above the seas links directly to the habitability of waters below, especially for larger and more active animals. Carbon dioxide in the Silurian atmosphere contributes strongly to the greenhouse character of the climate. Higher concentrations of this gas mean that more of the outgoing infrared radiation from Earth's surface is absorbed and re-emitted by the air, slowing the loss of heat to space. This helps maintain warmer average temperatures, especially at higher latitudes, and it supports the relatively high sea levels by reducing the volume of water locked into polar ice. Carbon dioxide levels are not fixed. They respond over millions of years to volcanic outgassing, from the interior weathering of rocks on land and burial of carbon in marine sediments. During the Silurian active mountain building and volcanic arcs supply gases to the atmosphere, while chemical weathering of exposed rock and the slow accumulation of carbon-rich deposits in the seas draw some of that carbon dioxide back out. The balance between these processes shifts gently over time, and the resulting air composition leaves its mark in the minerals that form and in the isotopic ratios preserved in rocks. Water vapour is another key component of this atmosphere, even though it makes up only a small fraction of the total mass at any given time. The amount of water vapour the air can hold rises strongly with temperature. In the warm Silurian world, especially over sunlit tropical and subtropical seas, evaporation loads the lower atmosphere with moisture. This moisture later condenses into clouds and precipitation, releasing latent heat that further powers atmospheric circulation. Over cooler, high-latitude waters and over the relatively bare continental interiors, humidity can be lower, leading to drier conditions and clearer skies, at least during certain seasons. Local and regional differences in water vapor content create contrasts in cloudiness and rainfall that help shape the surface environments without yet requiring a full description of wind patterns. The upper parts of the Silurian atmosphere participate in complex photochemical reactions driven by solar ultraviolet light. High-energy radiation splits molecules such as oxygen and water, producing reactive fragments that recombine into new species. One important product is ozone, which collects in a layer high above the surface. This ozone layer is thick enough to absorb a significant portion of the incoming ultraviolet flux that would otherwise damage biological molecules such as DNA. It reduces the harmful wavelengths that reach the sea surface and the very shallow waters, making it easier for organisms to live closer to the light. However, the shield is not perfect, and levels of ultraviolet radiation at the surface may still be higher than in some later periods, especially before plant cover becomes extensive on land and before certain feedbacks modify atmospheric composition. Tiny particles suspended in the air known as aerosols also shape the behavior of the Silurian atmosphere. Some of these particles originate from volcanic eruptions, which inject fine ash and sulfur-rich gases into the upper troposphere and lower stratosphere. There they can form droplets and crystals that reflect and scatter sunlight, slightly cooling the surface below for months to years after major eruptions. Other aerosols come from sea spray lifted from wave crests in the Panthalassic Ocean and in epicontinental seas, and from dust carried off dry continental interiors. The abundance and distribution of these particles influence cloud formation because they act as nuclei on which water droplets can condense. In this way, fine mineral grains and salt crystals help determine cloud brightness and lifetime, and so they adjust how much solar energy is reflected back to space. The overall pressure of the Silurian atmosphere at sea level is likely similar to or somewhat different from that of the modern atmosphere, but exact values are uncertain and depend on how much nitrogen and other background gases are present. Geological evidence provides broad constraints but not precise numbers. What is clear is that this air mass is thick enough to support a strong greenhouse effect when loaded with carbon dioxide and water vapor, and to allow winds and storms to move freely across the globe. The combination of gas composition, vertical structure pressure, and suspended particles sets the stage on which heat is transported, clouds form and precipitation falls. In turn, these atmospheric properties govern how energy from the sun is redistributed from equator to pole, and from ocean to land, shaping the boundaries of climate zones and the nature of day-to-day weather. The detailed patterns of those zones, the paths of winds and the locations of storm tracks follow from this structure, and arise from the way this layered, chemically active shell of air interacts with the spinning ocean-covered surface below. In the Silurian world, the pattern of climate arises from the balance between incoming solar energy, the composition of the atmosphere, the layout of oceans and continents, and the steady rotation of the planet. Because most land lies in the southern hemisphere, and much of it occupies higher latitudes while broad oceans dominate low, and mid-latitudes heat is taken up and released in an uneven way across the globe. Tropical belts of open Panthalassic Ocean and flooded continental shelves absorb large amounts of solar radiation. Warm surface waters and the air above them become key sources of heat and moisture for the atmosphere. Closer to the poles, especially around the southern margins of Gondwana, early in the period lower sun angles, and a history of ice cover help keep average temperatures cooler, even as long-term warming reduces permanent ice. This gradient from warm equatorial regions to cooler poles drives a basic system of atmospheric circulation. Around the equator, intense heating of the surface warms the air and causes it to rise. As it lifts, it expands and cools, and water vapor condenses into clouds and frequent showers or storms. This rising branch of motion forms the core of a circulation cell in each hemisphere, where air ascends near the equator, flows poleward aloft, sinks in the subtropics, and then returns toward the equator near the surface. These overturning structures, often called Hadley cells in modern climate science, are also present in the Silurian, though their exact width and strength depend on the distribution of land and sea, and on the level of greenhouse warming. Because the planet spins somewhat faster than in later eras, the deflection of moving air by the Coriolis effect is slightly stronger. Air that flows away from the equator is turned eastward in the upper troposphere, helping to form high-level westerly winds in mid-latitudes. Near the surface, the return flow toward the equator is turned westward, supporting persistent tradewind belts that blow from the subtropics toward the equatorial zone. Over the wide tropical oceans and epicontinental seas, these trades encourage the formation of long-fetch waves and help drive surface currents, but their main role in this section is as transporters of heat and water vapor within the air. In the subtropical zones of each hemisphere, where air from higher levels sinks back toward the surface, the climate tends to be drier and more stable. Sinking air warms as it compresses, reducing relative humidity and inhibiting cloud formation. Over open ocean, these regions may host broad areas of low cloud or clear skies and modest rainfall, while over land they favour the development of arid belts. In the Silurian, many of the continental interiors that lie within these latitudes are already dry for other reasons, including their distance from moisture sources and the absence of dense vegetation, so the subtropical circulation reinforces that dryness. Large areas of Gondwana's interior, far from coasts and at roughly comparable latitudes, experience limited rainfall and large temperature swings between day and night. Dust raised by winds over these bare or sparsely covered surfaces can be carried into the atmosphere and transported downwind, where it may later influence cloud properties and deposit minerals into the seas. Farther poleward in mid-latitude belts, the meeting of relatively warm air from lower latitudes and cooler air from higher latitudes produces strong horizontal temperature gradients. These contrasts are fertile ground for developing travelling storm systems. Waves in the upper level westerly flow grow and deepen, forming low-pressure centres, with fronts that sweep across ocean basins and continental margins. In the Silurian, the broad Panthallassic Ocean provides a long path for such storms to grow, while the arrangement of continents in the northern hemisphere introduces some disruption and local structure as systems move over land and shallow seas. These mid-latitude cyclones bring variable weather with periods of cloudiness, rain, and shifts in wind direction interspersed with calmer intervals. Over time, the repeated passage of such systems redistributes heat poleward and drives precipitation patterns that shape erosion on land and sediment input to coastal environments. At higher latitudes, especially near the southern polar regions around Gondwana, the air remains cooler and often more stable, though the details change as ice retreats. The contrast between cold polar air and milder mid-latitude air can support a persistent belt of stronger winds and storms, similar in function to a polar front. When significant sea ice or snow-covered land is present, the underlying surface reflects more solar radiation, keeping the region colder and maintaining sharp thermal boundaries. As climate warms and ice patches shrink, these contrasts may soften somewhat, but there is still a tendency for stronger winds and more frequent disturbances around the margins of the polar zone. These patterns influence how quickly heat from lower latitudes can reach the far south, and how much moisture falls as snow or rain on remaining glacial remnants and on highlands. Seasonal changes modulate this entire structure. Because Earth's axis is tilted, the hemisphere leaning toward the sun during its summer receives more direct sunlight and experiences longer days, while the opposite hemisphere receives less. In the Silurian, this leads to seasonal migration of the zones where air rises most intensely and where rainfall is frequent. The tropical rain belt shifts north and south over the year following the region of maximum heating. Monsoon-like circulations may develop where large land masses sit in the path of this shifting heat source, especially along the margins of Gondwana and the northern continents. In warm seasons, land surfaces heat more rapidly than adjacent seas, drawing moist air inland and leading to intensified rainfall near coasts and long river basins. In cooler seasons, the direction of surface pressure gradients changes, and drier, cooler air can flow outward toward the sea. Even without dense vegetation to trap moisture and influence local humidity, these seasonal wind reversals imprint recognizable wet and dry phases on certain regions. Storm tracks also wander with the seasons moving equatorward in winter and poleward in summer, which alters where mid-latitude systems deliver their rain and snow. The overall warmth of the Silurian greenhouse state means that global average temperatures are higher than in some earlier icehouse intervals, and permanent ice is restricted mainly to parts of the southern high latitudes early in the period. As warming continues and ice retreats, the albedo or reflectivity of those regions decreases, allowing more solar energy to be absorbed. This amplifies warming locally, and at times may weaken the equator to pole temperature gradients slightly, which in turn can affect the strength and position of westerly winds and storm tracks. Nevertheless, the broad pattern of warm tropics, cooler poles and atmospheric cells that carry heat from low to high latitudes remains a defining feature. Over the epicontinental seas and shallow shelves, the interplay of winds and surface temperatures creates zones of enhanced evaporation and precipitation. Persistent winds can draw moisture off warm waters and transport it inland, or they can drive dry air from continental interiors over the sea, changing patterns of cloud cover. In some coastal regions, especially where winds blow parallel to shorelines and interact with ocean currents, bands of low clouds and fog form. These features influence how much sunlight reaches the surface locally and affect the thermal environment of nearshore waters that later become important for reefs and shallow marine communities. All of these atmospheric motions operate on a background set by longer-term climate trends within the Silurian. Short-lived fluctuations in carbon dioxide and other greenhouse gases, perhaps linked to pulses of volcanic activity or changes in the burial of organic matter, can nudge temperatures up or down on timescales of hundreds of thousands to millions of years. Such shifts may slightly rearrange the positions of climate belts and alter the typical strength of winds and storms. However, within the period as a whole, the planet retains a generally warm character, with an active circulating atmosphere that continuously moves heat, moisture, and momentum from one region to another. The resulting pattern of climate belts, prevailing winds, and storm tracks forms the dynamic link between the outer energy balance and the ocean surfaces and landforms below, where sea levels, waves, and currents respond to the constantly changing push and pull of the air above. In the Silurian greenhouse world, sea level stands high enough that the outline of the continents is blurred by water. The volume of ice stored on land is small compared with some earlier times, especially after the Ordovician glaciation wanes, so little seawater is locked up in polar ice sheets. As the climate warms and ice retreats from much of southern Gondwana, meltwater returns to the ocean basins and raises global sea level. The exact height varies over millions of years, but throughout most of the period the seas are deep enough to flood broad regions of low-lying continental crust. Along the edges of Gondwana, Laurentia Baltica, and the smaller block shallow marine water covers areas that would stand above sea level in colder intervals. These drowned margins are known as epicontinental seas, meaning seas that lie on top of continental crust, rather than in the deeper basins between continents. They are typically no more than a few tens of meters to perhaps a couple of 100 meters deep, with gentle slopes that extend far inland from the true continental edge. Global sea level is not set only by the amount of ice. It also responds to the shape and volume of the ocean basins themselves, which are governed by plate tectonics and the state of the oceanic crust. Where new oceanic lithosphere is produced along mid-ocean ridges, hot buoyant material stands higher than older cooler crust farther away. This reduces the volume available for seawater and tends to raise global sea level. During the Silurian spreading rates and the arrangement of ridges and subduction zones combine to produce basins that are not at their largest possible capacity. Elevated ridge systems occupy a significant fraction of the seafloor, so even without extreme warmth, the baseline sea level would likely be above that of some later times, when ridges are cooler and deeper. As the warm climate and tectonic state reinforce each other, more water spills onto the continents. The Panthalassic Ocean, which fills most of the space between Gondwana and the northern continental blocks, has a structure that reflects these processes. In its central regions, the ocean floor lies at depth of several kilometers below the surface, covering old, dense lithosphere that has cooled and subsided. Long ridges and fracture zones cut across this deep floor, but these irregularities occupy only a small fraction of the total area. Closer to the continents, the seafloor rises along broad continental margins that gently arch upward from deep oceanic crust through transitional zones and onto true continental crust. In the Silurian, many of these margins are passive in the sense that there is little active subduction directly at the edge. Instead, they record earlier rifting and now subside slowly under the load of sediments and the weight of the water itself. The flooded shelves of these passive margins can extend for hundreds of kilometers from the coastline toward the deep basin. Their surfaces are low relief with subtle undulations incised ancient river valleys and the initial forms of deltas now drowned under marine water. Sea level stands high enough that many former lowland plains are underwater, turning what were once connected continental surfaces into archipelagos of islands and peninsulas surrounded by shallow seas. Not all basin edges are passive. In some regions, such as where Baltica and Laurentia interact, or where arcs and small plates converge with Gondwana active margins, host subduction zones. Here one plate is forced beneath another, creating deep oceanic trenches adjacent to rising mountain belts. The trenches themselves are narrow, but very deep depressions in the seafloor, while inland from them uplift produces volcanic arcs and deformed crust. These active zones locally reduce the area of shallow shelf, replacing it with sharp gradients in depth and complex topography. However, in the global picture of the Silurian oceans, the wide epicontinental seas on passive margins and interior platforms remain the dominant shallow water feature. The shape of Silurian basins and shelves changes gradually over time as tectonic plates continue to move and as the loads on the crust vary. Subsidence, which is the slow sinking of the crust under weight or due to cooling, creates accommodation space for sediments and seawater. Where subsidence outpaces sediment supply, water can maintain or increase its depth over a region, even as sediments accumulate. Where sediment input is high, as near active mountain belts, or large river systems, shallow seas may fill with sand, silt and mud, and their shorelines can migrate seaward or landward as the balance shifts. These processes occur on timescales of hundreds of thousands to millions of years, so they are not apparent on human timescales, but they gradually redraw the map of submerged and emergent land. Within the epicontinental seas, depth is typically shallow enough that waves and tides can stir the bottom at least in some zones. The interaction of wind-driven waves and daily tidal currents with the seabed sorts sediments by size and creates characteristic forms such as sandbars, shoals and tidal flats. In more protected settings, finer muds can settle. while in high-energy belts coarser grains dominate. The level of water above these surfaces depends on both global sea level and local factors such as subsidence and uplift. During the Silurian, as global conditions favour high sea level, many continental interiors experience extended intervals where shallow marine conditions persist, leaving long, nearly continuous records of shelf sedimentation. Small changes in global sea level, sometimes called eustatic changes, overlay this long trend. These shifts can be driven by short pulses of cooling or warming that alter residual ice volumes, or by changes in ridge volume and sediment loading. Even if the total range is only on the order of several tens of meters, such changes are enough to shift shorelines across wide, low-gradient continental platforms. When sea level rises, marine waters flood farther inland, depositing marine sediments over older coastal or terrestrial layers. When it falls, coastlines can retreat, exposing former seafloors to erosion or to non-marine processes. In the rock record, these repeated transgressions and regressions appear as stacked sequences where shallow water deposits overlie deeper water deposits and vice versa. In the Silurian, several such cycles are recorded, sometimes associated with minor disturbances in climate and biosphere. The relationship between sea level and climate is also mediated by the thermal expansion of seawater. Warm water occupies more volume than cold water, so as the greenhouse climate of the Silurian maintains relatively high global temperatures, the upper layers of the ocean are expanded compared with colder times. This effect adds a modest but real amount to sea level, augmenting the contribution from reduced ice volume. Conversely, any temporary cooling event that penetrates strongly into surface waters can lead to small but widespread contraction, lowering sea level slightly. Over millions of years, the combined outcome of thermal expansion ice volume changes, and tectonic control of basin capacity defines the history of Silurian sea level. In some regions, especially along the margins of Gondwana, where earlier glaciation carved deep valleys and fjord-like structures, residual topography influences how high seas interact with the continent. When sea level rises, these over-deepened valleys can fill with water to form narrow, elongated inlets that focus tidal and wave energy. When it falls, the same structures may become estuaries with strong salinity gradients, as rivers input fresh water at their heads. The presence or absence of ice nearby affects how much meltwater and sediment they receive, tying the local character of the shoreline to broader climatic conditions. The geometry of Silurian basins also sets the framework for later ocean circulation, but even without considering those currents, it is clear that the combination of high sea level and broad shallow shelves produces a planet where the boundary between land and sea is more diffuse than in many later ages. Continents are wrapped by extensive belts of marine water that reach far into their interiors. Only higher standing cratons and uplifted zones remain consistently above the waves. These topographic highs form the nuclei of emergent land, while surrounding lowlands experience repeated shifts between submergence and exposure. This pattern has important consequences for the future development of soil's early terrestrial ecosystems and the routes by which organisms may eventually move between marine and marginal environments. For now, the focus remains at the scale of sea and basin. Under a sky shaped by greenhouse gases and active circulation, the Silurian oceans fill deep basins and spill across subdued continental margins. High global sea level links distant regions through shallow seaways and epicontinental plains, while tectonic forces slowly alter the volume and shape of the containers that hold the water. The result is a world where vast areas of what will one day be land lie beneath relatively shallow seas, and where the distinction between ocean basin and continental surface is expressed not as a sharp line, but as a broad, gradually changing zone that extends from deep panthalassic waters across continental slopes and onto the wide sunlit shelves that define the next step inward. In the Silurian oceans, the upper layers of water form a complex but orderly structure that reflects the balance between solar heating, wind mixing, and the geometry of basins and shelves. At the broadest scale, the surface of the Panthalassic Ocean is warmest in the equatorial and low-latitude belts, where sunlight arrives most directly, and where skies are often clear or only partly clouded. Here, a sunlit skin of water absorbs energy during the day and then slowly releases it upward to the atmosphere and downward into deeper layers. Because water can store large amounts of heat, this surface zone acts as a buffer that smooths rapid temperature changes and helps sustain a relatively stable climate over seasons and longer intervals. Moving toward higher latitudes, the angle of incoming sunlight decreases and more energy is reflected rather than absorbed, so surface waters gradually cool. This latitudinal gradient in temperature sets up density differences in the upper ocean, because warm water is less dense than cool water. As a result, in many regions, a layered structure develops with a lighter, warmer surface layer riding above a cooler, heavier interior. The boundary between these layers, where temperature and density change most rapidly with depth, is known as the thermocline. In the Silurian Panthalassic Ocean, the depth and strength of this thermocline vary from place to place and from season to season. In tropical and subtropical regions, persistent heating from above and relatively gentle winds can maintain a fairly sharp thermocline at a modest depth, keeping the warm mixed layer relatively shallow. In mid and higher latitudes, stronger winds and storms stir the upper ocean more vigorously, deepening the mixed layer and sometimes eroding the thermocline during colder seasons as cooler, denser surface water sinks and mixes with underlying layers. The action of winds on the water surface also generates currents both at the very top as drifting films and beneath as more organized flows. Trade winds near the equator push surface waters westward, while westerly winds in mid-latitudes drive them eastward. Interactions between these wind-driven flows and the rotation of the planet deflect currents to the right in one hemisphere and to the left in the other. This produces broad gyre-like circulations in the open ocean, where surface waters follow curved paths that loop around high-pressure centres in the atmosphere. In the Silurian, the exact shapes of these circulation cells are influenced by the arrangement of continents and by the presence of wide gateway passages between basins, but the general pattern of large rotating systems that transport warm water, poleward along western boundaries, and return cooler water equator, word along eastern margins is already in place in some regions. Over the drowned continental shelves and epicontinental seas, the behaviour of the upper ocean is somewhat different from that of the deep Panthalassic interior. Water depths are much shallower, so wind and tidal mixing can extend through a large fraction of the water column, sometimes from surface to sea floor. In these settings, the thermocline may be weak or absent for much of the year, especially in higher latitudes or in areas exposed to strong and frequent storms. Instead, water temperature can follow the seasonal cycle of air temperature more closely, warming throughout the shallow column in summer and cooling in winter. Where these seas lie in tropical and subtropical belts, strong solar heating can still produce a warmer surface layer, but tidal currents and wind-driven circulation often limit the degree of stratification. The interaction between tides and basin geometry in epicontinental seas is important. Because these seas are shallow and can extend far inland, the tidal wave raised by the gravitational pull of the moon and sun can be amplified or damped depending on the shape of the seafloor and the coastline. In some embayments, this leads to strong tidal currents that run through narrow passages and over shallow bars, stirring the water and transporting sediments. In other regions, tides are weaker and their influence on mixing is smaller. Overall, however, the combination of tides and winds ensures that many Silurian shelves maintain good vertical exchange between surface and bottom waters, at least in open marine areas, which helps distribute heat, oxygen and nutrients through the shallow column. River inputs add another layer of complexity to the surface ocean structure, particularly along the margins of Gondwana and the northern continents, where rainfall feeds streams that drain into the seas. Fresh water from rivers is less dense than the salt water of the ocean, so it can form low salinity plumes that spread out over the surface near coasts. These plumes can stratify the upper few meters to tens of meters of the water column, especially during periods of high runoff. In warm climates such as those common in the Silurian, this fresh surface layer may heat up quickly under the sun, further enhancing the density contrast with underlying saltier water. Where mixing is limited, this can create a stable two-layer system with a thin, warm, less saline surface lens, capping cooler, saltier water below. Over time, winds, tides, and larger-scale circulation usually break down these structures, integrating fresh water into the broader ocean, but while they last, they influence local temperature and nutrient distributions and the habitats available for early coastal ecosystems. Salinity itself varies across the Silurian oceans. In the open panthalassic interior, far from large sources of freshwater, evaporation and precipitation largely determine surface salinity. Regions under subtropical high-pressure belts where skies are often clear and evaporation exceeds rainfall tend to develop higher surface salinities. Closer to the equator, where frequent showers and storms add fresh water from above, salinity may be lower. In epicontinental seas, the balance among river input, rainfall, evaporation, and exchange with the open ocean controls salinity patterns. In some restricted basins with limited connection to the wider ocean and strong evaporation, salinity can rise well above average, creating conditions favourable for the formation of evaporate minerals when water becomes saturated with dissolved salts. In other shallow, well-connected seas with ample freshwater input, salinity may remain slightly lower than the global mean. These gradients in salinity, together with temperature, set the density structure of surface waters and influence how and where they sink or rise. The upper ocean of the Silurian also contains suspended and dissolved materials that affect its physical behaviour. Fine mineral particles from dust and river-borne sediments, along with organic particles from plankton and decaying organisms, change the way light penetrates into the water. In clear tropical waters over carbonate shelves and open ocean gyres, light can reach tens of meters to even greater depths, sustaining photosynthesis over a thick surface layer and contributing to a deeper mixed zone. In more turbid coastal and epicontinental settings, where sediments and plankton are more abundant, light is absorbed and scattered in the upper few meters, limiting the depth of the most active biological and physical interactions with sunlight. This vertical distribution of light helps define the structure of the euphotic zone, the layer where photosynthesis is possible, and below that the darker zone where only scattered light remains. Heat transfer within the surface ocean is closely connected to the exchange of energy with the atmosphere. When warm, moist air passes over cooler water, heat and some moisture move from the air into the sea, cooling the atmosphere and warming the surface ocean. When cold, dry air flows over warmer water, heat moves from the sea into the air, sometimes producing fog or low clouds and driving convection in the lower atmosphere. In stormy regions such as mid-latitude belts, where travelling cyclones are frequent, strong winds and waves enhance these exchanges by increasing the area of contact and breaking up the surface. Over time, these processes help maintain relatively smooth horizontal temperature gradients, compared with what would exist if each region responded only to local solar heating. They also connect the behaviour of the surface ocean directly to weather systems, making the upper layers of the Silurian seas an active participant in the climate, rather than a passive background. Differences between the deep panthalassic ocean and the wide epicontinental seas become important when considering how quickly the surface responds to changes in atmospheric forcing. The deep ocean has enormous thermal inertia, so changes in surface temperature can take a long time to propagate into its interior. Epicontinental seas with their limited depth adjust more rapidly. A sequence of warmer years may raise the temperature throughout a shallow basin more uniformly, while the deep ocean shows a slower, more muted response. Conversely, short cooling events, perhaps driven by volcanic aerosols in the atmosphere, or by brief dips in greenhouse gas levels, can chill shallow seas relatively quickly, altering their density structure and circulation while the deep interior remains buffered. Thus, even though the same winds blow over both, the timescales of adjustment differ. This difference in response will later have consequences for the stability of environments on shelves and reefs. But at the level of physical structure, it simply reflects the contrast between deep stratified panthalassic waters and the more responsive variably mixed epicontinental seas that lie draped across the edges of the continents in the Silurian world. Across the Silurian world, the wide sunlit shelves and reef belts that fringe the continents form the main interface between the open ocean and the solid earth. In these shallow seas, light from the sun can penetrate all the way to the seafloor in many places, especially where waters are clear and where the bottom lies only a few tens of meters below the surface. This light supports active photosynthesis by microscopic algae suspended in the water and by simple plant-like organisms attached to the seafloor. It also provides the energy needed for organisms that build hard skeletons of calcium, carbonate the mineral that forms limestone, to grow and maintain their structures. The result is a mosaic of environments that range from wave-swept outer shelves and reef crests to quieter lagoons, tidal flats and protected embayments, all responding to the same basic controls of depth, light water motion, and sediment supply. On the outer parts of many Silurian shelves where water depth lies within the reach of fair weather waves and storm-driven swells, reef systems develop in bands that roughly follow the contours of the flooded continental margins. These reefs are not built by the same organisms that dominate modern tropical reefs, but they serve a similar physical role as rigid three-dimensional frameworks that rise above the surrounding seafloor. The main builders are tabulate corals, which are colonial animals with flat, closely packed corallites, and stromatoporoids, which are sponge-like organisms that secrete massive layered skeletons of calcium carbonate. Together they form solid structures that can grow vertically and laterally over time as colonies expand and as new generations cement themselves onto older skeletons. Other organisms such as solitary rugose corals, calcareous algae, and various encrusting forms contribute to filling gaps and binding the framework. The position and shape of these reefs are controlled by a delicate balance between wave energy and water depth. On the seaward side, strong wave action can break and erode fragile structures, while on the landward side, water may become too restricted or too turbid if too much fine sediment arrives from rivers or resuspended muds. The most robust reef growth often occurs in zones where wave energy is high enough to keep the water well mixed and clear, but not so intense that it constantly destroys the framework. In these settings, water moving back and forth over the reef crest brings a steady supply of oxygen and dissolved ions, while removing waste products supporting rapid carbonate accumulation. Storms play an important part in shaping these outer shelf environments. When large storm systems pass overhead, pressure drops and winds drive strong waves and surges that reach deeper than during normal conditions. These events can break off blocks of coral and stromatoporoid skeletons and move them landward or downslope. They may also generate density-driven currents that carry sand and gravel into deeper parts of the shelf. Over many such episodes, a characteristic pattern of deposits forms with reef cores made of more massive and coherent skeletons, flanked by aprons of broken debris and graded beds that record storm influence. Even though individual storms are brief, their cumulative effect over millions of years is to sculpt the geometry of the reef belts and adjacent seafloor. Landward of the main reef crests, where waves are partially broken and energy is reduced quieter, water bodies develop. These can take the form of lagoons, which are shallow enclosed or semi-enclosed areas behind the reef line, or of broad inner shelves with gentle slopes. In these regions, the seafloor experiences less constant agitation by strong waves, though it may still feel the pulses of storms and tides. Sediments here are commonly composed of finer carbonate muds mixed with sand-sized grains that originate from the breakdown of shell skeletons and chemical precipitation. In very clear, warm and agitated waters, these sand grains can take on a distinctive rounded form known as oolitic texture, where concentric layers of calcium carbonate grow around small nuclei as grains roll back and forth on the seabed. Such oolitic shoals are common features of Silurian shallow marine deposits and tend to form in belts where currents and waves are strong enough to keep grains in motion, but not so strong as to sweep them away entirely. In more protected parts of lagoons and inner shelves, carbonate mud can settle from suspension, forming soft, fine-grained layers on the bottom. These muds may be bound together by microbial films and by the root-like structures of simple bottom-dwelling organisms. Over time, they can lithify into macritic limestones which preserve traces of burrows feeding trails and the remains of small shells. The distribution of grain sizes and the presence or absence of features such as crossbedding, ripple marks and burrow structures in these sediments record the range of energies and biological activities that occur in different parts of the shallow system. Tidal processes add another rhythm to these sunlit shelves. As the gravitational pull of the moon and sun raises and lowers water levels, tides generate currents that flow in and out of embayments, lagoons and along coastlines. In some Silurian settings, especially where shelf geometry focuses these motions, tidal ranges can be significant. The associated currents sculpt tidal channels, bars and flats. On sandy substrates, migrating dunes and ripples leave packages of inclined laminae that later become cross-bedded sandstones. On muddier substrates, tidal flats experience alternating exposure and flooding, producing cracked, desiccated surfaces in some seasons, and soft waterlogged muds in others. The upper parts of these flats may be colonized by microbial mats and small pioneering plants and fungi near shore. But the main story at this stage remains the interaction between water and sediment. In addition to pure carbonate systems, some Silurian shelves receive a noticeable supply of siliciclastic sediment, a term that covers grains derived from the breakdown of silicate rocks, such as sandstones, siltstones, and shales. Along the margins of continents where rivers drain actively eroding uplands and mountain belts, fans, deltas, and shorelines deliver sand and mud to the shallow seas. In such mixed systems, reef growth may be limited to clearer sectors, while other areas are dominated by sandy shore face environments or by muddy offshore shelves. The relative balance between carbonate production by marine organisms and chemical precipitation and siliciclastic input from land governs which type of sediment dominates at any given time and place. This balance can shift as climate, sea level, and tectonic activity change. For example, a period of uplift and increased erosion in a nearby mountain belt might temporarily increase siliciclastic delivery, smothering some carbonate-producing communities and promoting more terrigenous deposits, while quieter tectonic intervals allow carbonate factories to expand across clearer waters. The chemical conditions in these shallow sunlit waters are generally favourable for carbonate precipitation. Warm temperatures, relatively high carbon dioxide in the atmosphere, and active photosynthesis combine to make seawater often supersaturated with respect to calcium carbonate near the surface. As photosynthetic organisms remove dissolved carbon dioxide during the day, they slightly increase the saturation state in their immediate surroundings, making it easier for skeletons to grow and for fine carbonate mud to precipitate. At night, when respiration dominates, local conditions are different. but the overall daily cycle still tends to favour net carbonate accumulation in many reef and lagoonal settings. Variations in water circulation, such as restricted exchange in certain embayments, can modulate this pattern by altering temperature, salinity, and the build-up of metabolic byproducts. Across the Silurian shelves, light and clarity of water set a practical limit to how deep active reef building and phototrophic carbonate production can extend. In the clearest tropical waters, this depth can reach several tens of meters, but in more turbid zones near river mouths and along mixed sediment coasts, the effective photic zone, meaning the layer where enough light exists for significant photosynthesis, may be only a few meters thick. Below this depth, carbonate sedimentation can continue through other processes, but the main contribution from light-dependent organisms declines. Thus, the vertical range of the sunlit shelf is not simply a matter of absolute depth, but also of water transparency, which itself responds to sediment input, plankton abundance, and the degree of water motion. The geometry of Silurian shallow seas often includes subtle breaks in slope and localized highs that influence how these environments are arranged. Low-relief carbonate platforms can develop where much of the surface lies within a narrow depth interval. On such platforms, large portions of the seafloor are bathed in similar light and energy conditions, allowing extensive lateral continuity of faces, a term for bodies of rock with distinct characteristics. At the edges of platforms, steeper slopes drop toward deeper basins, and here debris from the upper surface can move downslope as gravity-driven flows forming talus and breccia deposits. Farther landward toward the interface with truly terrestrial environments, water depth decreases and wave energy frequently reaches the bottom. This nearshore zone can host beaches and barrier systems composed of reworked skeletal material and other sand-sized grains. In some regions, storms and tides breach these barriers, linking lagoons and open sea, and allowing periodic flushing that prevents extreme stagnation. In other more restricted areas, circulation is weaker, and bottom waters may occasionally become low in oxygen if organic matter accumulates faster than it can be decomposed under fully oxygenated conditions. Such restricted, shallow basins are potential sites for unusual chemical deposits and for the preservation of fine lamination in sediments. Through all of this, the controlling factors remain the same: depth, distance from open ocean energy, of waves and tides, clarity and chemistry of the water, and the slow, steady adjustment of sea level and basin shape. The Silurian sunlit shelves and reefs are not uniform along every coastline, but taken together, they form a broad, interconnected realm of clear, warm, shallow water environments. They are the zones where the interaction between solar energy seawater and solid earth is most intense, and where a large fraction of the period's carbonate sediments and many of its most distinctive structures accumulate. Beyond their outer edges, the seafloor slopes into deeper, dimmer waters, where different processes dominate, while toward land their upper margins grade into tidal flats, shoals, and eventually the first persistent terrestrial surfaces. Below the well-lit zones of the Silurian shelves and reefs, the seafloor descends into environments where light fades, temperatures drop, and the character of the sediments changes. Moving outward from the shallow platforms, the bottom passes through an outer shelf belt, then across the upper continental slope, and eventually onto the deep basin floor of the Panthalassic Ocean and of smaller marginal basins. In these deeper settings, waves generated by everyday winds no longer reach the bottom, and only the larger storms can stir the near bedwater for short intervals. Currents are generally slower and more uniform, driven by the large-scale circulation of the ocean and by the slow sinking and spreading of denser water masses formed at the surface. As a result, much of the sediment that accumulates here arrives as a steady, quiet rain of fine particles from above mixed with occasional pulses of coarser material delivered by gravity-driven flows from shallower regions. The transition from inner to outer shelf is not marked by a sharp boundary, but by a gradual deepening beyond the zone where strong fair weather waves mobilize the bed. On the outer shelf, storm waves can still influence the seafloor during energetic events, delivering sand and shell fragments downslope and generating temporary resuspension of mud. Between storms, however, fine silt and clay-sized particles settle through the water column and form a drape over older, more energetic deposits. The proportion of carbonate to siliciclastic material changes with distance from shore and with the productivity of carbonate factories landward. In many Silurian basins, outer shelves are dominated by fine carbonate muds derived from the breakup of skeletal debris and from chemical precipitation, with only a modest contribution from land-derived clastic grains, except near large river systems. Where continents supply more siliciclastic sediment, perhaps along active or rapidly eroding margins, the outer shelf may host thicker accumulations of siltstones and fine sandstones that grade basinward into shales. Farther down the slope, gravity processes become more important. As sediment builds up on upper slopes and shelf breaks, it occasionally fails, sending down dense sediment-laden flows known as turbidity currents. These currents travel downslope under the influence of gravity, carrying sand, silt, and mud into deeper water. When they lose momentum, they deposit their load in characteristic beds that fine upward from coarser material at the base to finer at the top. Over time, stacked sequences of such beds form turbidites which record repeated episodes of slope instability and sediment delivery from shallow to deep environments. In the Silurian, turbidite systems operate along the edges of many basins, especially where tectonic uplift, high sediment supply, or rapid sea level changes promote oversteepening of slopes. These deposits provide a pathway by which shelf-derived carbonate and siliciclastic material reaches the deeper parts of the ocean, influencing the composition of basin floor sediments. Beyond the reach of most coarse gravity flows, the deep basin floor receives a more evenly distributed supply of fine particles. The largest component is often clay and silt derived from the breakdown of continental rocks, carried out to sea by rivers, and kept in suspension by currents until they eventually settle. Mixed with this terrigenous material are tiny skeletons of planktonic organisms and fine carbonate mud that slips off shelves or precipitates directly in the water column. The proportions of these components vary with distance from land, with ocean productivity, and with water depth. In regions far from significant landmasses where water is clear, and plankton productivity is moderate, deep-sea sediments may take the form of carbonate-rich mudstones with scattered shells. Closer to continents or under zones of higher nutrient supply, they may contain more clay and organic matter, forming grey or dark-coloured shales. Oxygen levels in the deeper Silurian Ocean are not uniform. Near the surface and on well-mixed shelves, waters are supplied with oxygen from the atmosphere and from photosynthesis. As these waters sink and move into deeper layers, they carry dissolved oxygen with them. At the same time, organic material produced in the surface ocean falls through the water column and is decomposed by microbes, a process that consumes oxygen. Where the rate of oxygen supply by circulation balances or exceeds the rate of consumption, deep waters remain oxygenated, and sediments that accumulate on the seafloor are laid down under fully aerobic conditions. In such settings, bioturbation by burrowing animals is common, mixing sediments and producing mottled fabrics rather than sharp lamination. Where circulation is weaker or organic matter flux is higher, however, oxygen can become scarce at mid-depths or near the bottom. In these oxygen minimum zones, the water column supports fewer large animals, and the seafloor is colonized by organisms that tolerate low oxygen or by microbial communities that use alternative electron acceptors for respiration. If oxygen levels fall very low or reach nearly zero, conditions become anoxic. Under anoxic bottom waters, organic matter is preserved more effectively in sediments because it is not fully oxidized. Sulfate-reducing bacteria use sulfate from seawater as an oxidant instead, producing hydrogen sulfide that can react with iron to form minerals such as pyrite. The resulting sediments are often rich in organic carbon and iron sulfides and appear dark grey to black when lithified, hence the term black shales. In the Silurian intervals of black shale deposition occur in various basins, sometimes correlating across large regions. They are interpreted as recording episodes when some parts of the ocean, particularly deeper or more restricted basins and outer shelves, experienced expanded low oxygen or anoxic conditions. The causes of these episodes likely involve a combination of high surface productivity, restricted circulation due to basin geometry, and changes in climate and sea level that alter the pattern of water mass formation. But the consistent point is that they mark times when deeper environments differed markedly from the well-ventilated shallow shelves and reefs. The presence of anoxic or poorly oxygenated zones also influences the vertical distribution of life and sedimentary structures. In oxygen-rich settings, burrowing benthic organisms churn the upper layers of sediment, disrupting lamination and creating complex networks of tunnels and feeding traces. In low oxygen settings, such activity is limited or absent, allowing fine laminations formed by settling particles to remain intact. When viewed in rock outcrops, these laminated shales and mudstones provide evidence of the quiet low-energy conditions that prevailed at the time of deposition and of the chemical state of the water column above. In some Silurian successions, sharp transitions occur between bioturbated lighter, coloured mudstones and darker laminated black shales, reflecting shifts between better ventilated and more stagnant conditions. These changes can be tied to relatively rapid environmental perturbations, such as short-lived sea level rises that flood additional shelf areas and enhance organic carbon burial, or to reorganization of circulation patterns. Along certain active margins and in foreland basins adjacent to uplifted mountain belts, deeper water sedimentation is further complicated by tectonics. Subsidence rates can be high, creating accommodation space for thick piles of deep marine sediments to accumulate. At the same time, proximity to uplifting source areas increases the supply of coarse material, leading to interbedded sequences of conglomerates, sandstones and mudstones deposited by submarine fans. These fans spread outward from canyon mouths at the base of the continental slope, building lobes and channels that shift position over time. Even in these more dynamic and variable settings, the general pattern holds. Coarser beds represent discrete delivery events, while finer mudstones represent the background settling of suspended particles between events. Overlying all these processes is the constant settling of microscopic skeletal remains known as biogenic rain. Planktonic organisms in the surface ocean, such as graptolites and other small plankton, produce skeletal elements that eventually sink after death. Some dissolve before reaching the seafloor, especially in deeper waters where pressure and chemistry make carbonate less stable, but others survive and contribute to the sediment. Siliceous skeletons, where present, follow similar paths. The differences in dissolution rates and in the abundance of various plankton groups with depth and time give rise to subtle compositional variations within deep-sea sediments. In some intervals, increased biogenic input yields more fossil-rich layers, while in others clay and silt dominate. Over millions of years, the accumulation of these deposits builds thick sequences on the basin floor and lower slopes. The rate of accumulation is usually slow, measured on human timescales, often only a fraction of a millimetre to a few millimetres per year, but over Silurian durations this steady pace produces substantial thicknesses. Compaction under the weight of overlying layers expels pore water and brings grains closer together, while chemical reactions alter minerals. clay minerals may recrystallize organic matter, may transform and release fluids, and carbonate can dissolve in one zone and reprecipitate in another. The end result is a suite of lithified rocks ranging from limestones and dolostone to mudstones and shales, each carrying a record of the physical, chemical, and biological conditions under which they formed. The transition from shelf to deep basin in the Silurian Ocean is thus expressed as a change from high-energy light-filled settings dominated by skeletal carbonate production to low-energy, darker settings dominated by fine particle settling, episodic gravity flows and varying degrees of oxygenation. Each environment leaves its own characteristic imprint in the sediments that cover the seafloor, providing a layered archive of the ways in which particles have moved through the ocean and settled onto the bottom during this period. From outer shelf muds to slope turbidites and basin plain shales, the deeper environments knit together material from many sources above, integrating signals from climate tectonics and biological activity into the quiet, slowly accumulating record of the Silurian deep sea floor. In the Silurian, the solid outer shell of Earth continues to move in slow, persistent ways that reshape ocean basins, build mountain ranges, and create the depressions where sediments and seas can gather. The crust and uppermost mantle are divided into rigid plates that slide past, collide, and pull away from each other over the softer convecting interior. These motions are too slow to notice over human lifetimes, but over millions of years they change the map of continents and oceans in ways that control where shallow seas spread, where deep basins open, and where land is uplifted into highlands. At this time, one of the most important tectonic stories unfolds in the Northern Hemisphere. Several continental blocks that once lay far apart begin to converge and interact as the ocean that separated them, often called the Iapetus Ocean, in later reconstructions continues to narrow. Laurentia, which includes the cores of later North America and Greenland, moves toward Baltica and toward a smaller block known as Avalonia. As these plates approach subduction zones along the ocean margins, draw down oceanic crust, consuming it and pulling the continents closer. Above the subduction zones, volcanic arcs rise as melting in the mantle produces magma that ascends and erupts at the surface. These arcs may take the form of chains of volcanic islands or of coastal mountain belts built on continental crust. As convergence proceeds, collisions begin. When a buoyant continent or island arc reaches the subduction zone, it resists being pushed down into the mantle. Instead, the zone of convergence thickens, rocks deform, and portions of the crust uplift. This process of mountain building is known as orogeny. During the Silurian, a major orogenic system takes shape as Laurentia Baltica and Avalonia progressively collide, forming what will become part of the old core of Europe and eastern North America. Later geologists refer to aspects of this history as Caledonian-style orogeny. From a Silurian perspective, the outcome is a belt of rising mountains, deformed rocks, and associated basins that stretches across large parts of the Northern Hemisphere. As crust is shortened and stacked in the collision zone, it thickens, and thicker crust floats higher on the mantle, creating elevated regions. At the same time, the weight of these growing mountains pushes down the lithosphere on either side, creating flexural depressions known as foreland basins. These basins develop adjacent to the orogenic core and subside as more material is added to the mountain belt. Rivers draining the rising highlands carry sediment into these basins, filling them with a mixture of coarse and fine deposits that record the erosion of the mountains and the progressive advance of the deforming front. In some areas, these fallen basins connect with the shallow, epicontinental seas that cover continental interiors, so marine waters flood into them from the seaward side while sediment arrives from the landward side. This arrangement leads to complex patterns of shoreline movement and to thick wedges of Silurian sediment that thin away from the orogenic belt. Within the mountain belts themselves, rocks that were once laid down as sediments on ocean floors or continental margins are now buried heated and squeezed. Under these conditions they undergo metamorphism, meaning that their minerals realign, and new minerals form without melting. Sandstones can transform into quartzite shales, into slates and schists, and limestones into marbles. Folds and faults develop as layers are bent and broken. Some of these structures later control where fluids move, where minerals are concentrated, and how the crust responds to future stresses. During the Silurian, this deep crustal activity remains hidden beneath the surface, but its effects are expressed in the topography and in the patterns of uplift and subsidence that shape basins and coastlines. Along the southern edge of the Panthalasic Ocean, Gondwana remains a large, mostly coherent supercontinent, but its margins are not static. Subduction zones along parts of its perimeter generate volcanic arcs and accretionary wedges where slices of oceanic crust and sediment are scraped off and added to the continental edge. These processes thicken the crust in some regions and build coastal highlands. Elsewhere, where rifting and extension operate, new basins open as the crust stretches and thins. In such extensional settings, blocks of crust drop down along faults, forming grabens and half-grabens that can later be flooded by the sea. The pattern of extensional basins and collisional belts gives the Gondwanan margin a complex mix of rising arcs, stable cratons and subsiding shelves. The rate at which tectonic plates move is modest when measured in centimetres per year, but over the tens of millions of years that make up the Silurian, these movements add up. Continents that began the period at certain latitudes and orientations slowly shift. Laurentia drifts closer to the equator. Baltica continues its journey from higher southern to more equatorial or even northern positions, and smaller microcontinents adjust around them. These latitude changes alter the climates that different pieces of land experience because they move through the pattern of global climate belts shaped by solar input. A block that starts in cooler temperate latitudes and ends the Silurian closer to the equator experiences a transition toward warmer conditions, higher rates of chemical weathering, and different styles of sedimentation. Uplift and erosion in mountain belts play a major role in supplying material to the seas. Newly raised ranges expose fresh rock to the atmosphere and to circulating water. Chemical weathering processes break down minerals, consuming carbon dioxide from the air as carbonic acid in rainwater reacts with silicate rocks. The products of this weathering, including dissolved ions such as calcium and bicarbonate, flow into rivers and eventually reach the ocean, where they contribute to the pool of dissolved constituents used in carbonate formation. Solid particles ranging from clay to boulders also travel downstream, sorted by size as they move. Coarser material deposits near mountain fronts as alluvial fans and coarse deltas, while finer material reaches farther into epicontinental seas and deep basins. Thus, tectonically driven uplift feeds both ocean chemistry and sediment budgets, linking the behavior of the crust directly to conditions in the water above. Subsidence, the slow sinking of the crust, is equally important. In some Silurian regions, interior parts of continents that have cooled after earlier episodes of rifting and magmatism continue to subside gradually. This subsidence provides accommodation space for thick accumulations of shallow marine carbonates and mixed sediments. Without enough subsident sediments applied to a shelf might quickly fill available space and push shoreline seaward, but when the crust sinks at a rate similar to or slightly less than sediment supply, shallow marine environments can persist in roughly the same geographic area for long intervals. This stability favours the development of extensive carbonate platforms and reefs, as discussed earlier, and allows for the stacking of many similar depositional cycles in vertical succession. In contrast, where subsidence outpaces sediment input, water depths can increase over time, causing environments to shift from shallow to deeper settings and leaving more condensed records of shallow water facies. The interplay between uplift and subsidence also governs the formation of unconformities, which are surfaces in the rock record that represent gaps in time either due to non-deposition or to erosion. During the Silurian, regional uplift associated with orogeny or with flexural rebound can raise parts of the crust above sea level, exposing previously deposited marine sediments to sub-aerial weathering and erosion. Rivers cut into these uplifted areas, removing material and creating landscapes of valleys and ridges. Later, if sea level rises again or if subsidence resumes, marine waters can flood over these eroded surfaces, depositing new sediments on top. In the rock record, such unconformities appear as sharp boundaries between older, often tilted or eroded layers and younger, more gently dipping strata. They mark episodes when tectonics and sea level combine to alter the distribution of depositional environments. Volcanic activity tied to plate motions contributes gases and ash to the atmosphere and particles and lava to the surface. In arc settings above subduction zones, volcanoes erupt intermittently, sending plumes of ash into the air and depositing layers of volcanic material over land and into nearby seas. These ash layers can settle over wide areas as thin but widespread sheets, becoming bentonite beds in the rock record after alteration. They are important time markers because a single eruption can blanket large regions with a distinct layer that later helps link separate sedimentary sections. Submarine volcanism along mid-ocean ridges adds new basaltic crust to the seafloor, creating relief and influencing local circulation, though much of this activity takes place at depths and in locations that do not directly affect shallow Silurian environments. Over long spans, the balance between crust creation at ridges and crust destruction at subduction zones determines the average depth of ocean basins. A faster rate of ridge formation and higher ridge crests reduce the volume available for seawater and contribute to higher global sea level, while slower spreading and cooler, denser ridges increase basin capacity. In the Silurian, ridge systems are active enough that basin volume remains relatively modest, reinforcing the high sea levels already supported by warm climate and limited ice. Small-scale tectonic features such as faults and fractures also influence local basin development. Normal faults associated with extension create tilted blocks and half-grabens that can localize sedimentation and control the pathways of rivers and submarine channels. Reverse and thrust faults associated with compression stack slices of crust and create structural highs and lows. Strike-slip faults where blocks slide past each other can generate pull-apart basins in places where their trace bends or steps. Each of these structures can host distinct sedimentary packages and influence the preservation of environments. In some Silurian regions, small pull-apart basins along strike-slip systems may fill with restricted marine or even non-marine sediments, while nearby areas continue to host open shelf deposits. Through all these mechanisms, plate motions and crustal processes provide the slowly changing framework in which Silurian oceans and seas evolve. They decide where deep basins exist to receive fine sediments, where broad shelves form to host reefs and carbonate platforms, where coasts are stable and low, and where they are steep and active. The resulting pattern of uplifts, basins, and shifting coastlines is fundamental to how sediments accumulate, how sea level appears to rise or fall relative to land, and how the record of Silurian environments is preserved in the rocks that later observers study. Beneath the moving waters and changing climates, the deep, steady work of tectonics continues quietly arranging the containers and boundaries that make the period's oceans and seas possible. The Silurian world leaves its history in a thick-layered archive of rocks, where changes in sea level, climate, and life are recorded as variations in lithology, fossil content, and subtle shifts in the ratios of chemical elements. On broad continental shelves and in epicontinental seas, repeated cycles of flooding and retreat lay down alternating beds of limestone, dolostone shale, and occasional sandstone. In many regions, Silurian successions consist of stacked carbonate platforms separated by thinner intervals of more clastic-rich deposits, each package reflecting a phase when clear, warm, shallow seas spread over the continental surface, followed by a phase when conditions became somewhat deeper, muddier, or more influenced by land-derived sediments. These cycles often begin with relatively coarse or shallow water fesses, such as ripple-marked sandstones or cross-bedded grainstones pass upward into thicker limestones full of reef debris or shallow water fossils, and then grade into finer-grained mudstones and shales that represent slightly deeper, quieter water. At the top of some cycles, an erosional surface or a condensed horizon marks a pause or reversal, after which another transgression brings back shallow sea conditions. On the surfaces of platform carbonates, wave and current structures become frozen in place as sediment hardens. Crossbedding preserves the migration of subaqueous dunes and bars under tidal and storm-driven flows. Ripple marks record the interaction of oscillatory waves and currents with sandy bottoms. Hard grounds, which are seafloor surfaces cemented while still at or near the sediment, water interface can form during intervals of reduced sediment supply and continued chemical precipitation. These hard encrusted surfaces are colonized by borers and encrusting organisms before being buried by younger material. Their presence in Silurian sections indicates times when sedimentation slowed or stopped, briefly allowing the seafloor to stabilize and lithify. In some areas, thin beds of evaporate minerals such as gypsum and halite appear within mainly marine sequences. These layers form when seawater in restricted basins becomes sufficiently concentrated by evaporation that dissolved salts precipitate. Their occurrence signals episodes when parts of epicontinental seas or isolated embayments were cut off enough from open ocean circulation and experienced high evaporation rates, often under arid or seasonally dry climates. The alternation of normal marine carbonates, shales, and evaporates captures shifts in basin restriction climate and sea level. For example, a rising sea may connect a restricted basin more fully to the open ocean, replacing evaporitic conditions with normal marine sedimentation, while a falling sea or local uplift can isolate the basin again and renew evaporate deposition. Fossils are abundant in many Silurian rocks, and their distribution in vertical sequences offers another set of signals. Reef limestones and associated shallow water carbonates often contain dense assemblages of corals, stromatoporoids, brachiopods, crinoids, and trilobites. The species present their relative abundance, and their ecological associations change upward through the section as communities adapt to evolving conditions. Certain fossil groups appear or diversify in particular intervals, while others decline or vanish. Graptolites, which are colonial planktonic organisms preserved mainly in fine-grained offshore sediments, provide especially useful markers in deeper water successions. Their rapid evolution and wide distribution allow rocks from different basins to be correlated with relatively high precision. In many Silurian shales, distinct graptolite faunas define successive biozones, each representing a slice of time. By tying these zones to shallow shelf deposits through combined fossil and physical correlations, the rock record links environments across the shelf to basin gradient into a single temporal framework. Isotopic compositions of certain elements offer a more cryptic but powerful tool for reading Silurian conditions. Carbon isotopes in carbonate minerals and in organic matter, measured as the relative abundance of heavier and lighter forms of carbon, respond to changes in the global carbon cycle. When large amounts of organic carbon are buried in sediments, the remaining ocean and atmosphere become relatively enriched in heavier carbon, which is then recorded in carbonate skeletons and cements. Conversely, when stored, organic carbon is oxidized and returned to the system, the balance shifts back. In Silurian sections, long intervals of relatively stable carbon isotope values are punctuated by excursions, which are shifts toward more positive or more negative values over limited stratigraphic ranges. Some of these excursions coincide with black shale intervals, and with evidence for temporary oxygen depletion in parts of the ocean. They indicate times when organic carbon burial increased, possibly due to expanded productivity and stagnation in certain basins. Others occur alongside changes in fossil assemblages and in sediment type, suggesting broader reorganizations of climate and ocean circulation. Oxygen isotopes in carbonate skeletons and cements, although more challenging to interpret due to diagenetic overprinting, can carry information about water temperature and global ice volume. In general, heavier oxygen isotopes in marine carbonates can indicate cooler conditions or increased storage of light oxygen in ice, while lighter values can reflect warming and ice loss. In Silurian rocks, trends in oxygen isotopes across certain intervals, when considered with other evidence, suggest modest swings in temperature and in the extent of high-latitude ice even within the overall greenhouse state. These subtle changes may align with small sea level fluctuations inferred from facies shifts, reinforcing the picture of a climate system with shorter-term variability superimposed on longer-term warmth. Sulfur isotopes and trace metal concentrations also contribute to the picture of ocean chemistry and redox conditions. In anoxic basins where sulfate reduction is active, sulfur isotopes in pyrite and in coexisting sulfate minerals can record the balance between microbial processes and the size of the global sulfur reservoir. Elevated concentrations of redox-sensitive trace metals such as molybdenum and uranium in black shales point to conditions where deep or intermediate waters were oxygen poor for extended periods. When these geochemical indicators are aligned with the distribution of black shales with the degree of sediment lamination, and with the presence or absence of benthic fossils, they outline episodes when parts of the Silurian Ocean became more stratified and less oxygenated. These episodes do not necessarily represent global anoxia, but they mark important departures from fully ventilated conditions. Volcanic ash beds form another type of marker within Silurian sequences. These fine-grained layers, often a few centimeters to decimeters thick, show distinct mineral compositions and glass shard textures that reveal their pyroclastic origin. After deposition, they alter to clays, such as smectite, forming bentonite beds that stand out from surrounding carbonates and shales. Because a single explosive eruption can spread ash over large areas. In a short time, these layers act as nearly instantaneous timelines. Dating of minerals within some ash layers using radiometric methods provides numerical ages that anchor parts of the Silurian timescale. Correlating ash beds between basins ties together different depositional environments and helps synchronize records of local events with the global chronology. Minor extinction and faunal turnover events leave their own signals in the Silurian rock record. While the period does not end in a crisis on the scale of the Ordovician or later Devonian extinctions, there are intervals when certain groups decline or when community structures rearrange. These changes can be seen in the disappearance of particular fossil taxa from upward sequences, in shifts from one dominant group to another, or in reductions in diversity within specific habitat types. Sometimes these biological changes occur near horizons that also show changes in sediment-type black shale deposition, or isotope excursions, suggesting that environmental stresses such as oxygen depletion, sea level change, or climate fluctuation played a role. For example, a transgression that deepens shelf environments and expands low oxygen zones may reduce habitable space for some benthic communities while favouring opportunistic species able to tolerate new conditions. Erosional surfaces and hiatuses add to the complexity of the Silurian archive. where uplift or sea level fall exposes seafloors parts of the record can be removed. Channels cut into underlying sediments karst features develop in exposed carbonates due to dissolution by meteoric water and soils, or weathering horizons may form on top. Later transgression may flood these surfaces and bury them under new marine deposits. In the rock record, such surfaces appear as irregular, sometimes pitted or in filled contacts between older and younger units. They represent lost intervals of time and missing details, but they also mark key moments when tectonics and sea level change intersect, and when environmental conditions on land and in coastal zones differ from those recorded above and below. Viewing the Silurian stratigraphic record as a whole, the combination of lithologic stacking patterns, fossil assemblages and geochemical signatures captures a system that is generally warm with high sea levels and active carbonate production, but also punctuated by shorter intervals of relative cooling, sea level adjustment and changes in ocean oxygenation. Carbonate platforms expand and contract, black shales appear and disappear, evaporates form in restricted basins, and then give way to open marine conditions, and mountain building leaves its trace in foreland basins filled with thick clastic wedges. Each of these signals is local or regional in origin, but when correlated across many sites they outline global scale changes that ripple through the Silurian Earth system. The rocks do not offer direct images of ancient winds or currents, but their composition and structure encode the integrated effects of atmospheric circulation, climate belts, ocean stratification, and tectonic forcing. In this way, strata laid down in Silurian seas, lagoons and basins act as a physical record of the period's environmental behavior, preserving evidence of long stretches of relative stability, as well as the more abrupt adjustments that succeed one another through the tens of millions of years that make up this interval. In the Silurian oceans, the chemistry of seawater controls how carbon, nutrients and oxygen move through the system, and how the physical structures already describe support living communities. Seawater is a solution of many dissolved salts, but a few major ions dominate its composition. Sodium and chloride together make up most of the dissolved material and set the basic salinity. Other important ions include magnesium, calcium, sulfate, potassium and bicarbonate, which is a form of dissolved inorganic carbon. The relative proportions of these main ions are broadly similar to those of later periods, so Silurian seawater is still a mostly stable salty medium with a composition that changes slowly over geological time rather than rapidly from year to year. However, the absolute concentrations of some components differ from those of much later oceans, especially those tied to the long-term carbon and calcium cycles, and to the balance between seafloor spreading, weathering and sediment burial. The carbon system in seawater is central to many of these differences. Carbon dioxide from the atmosphere dissolves into the surface ocean, where it reacts with water to form carbonic acid, which then dissociates into bicarbonate and carbonate ions. Together these species make up the dissolved inorganic carbon pool. The ratios among them depend on temperature, pressure, salinity, and the alkalinity of the water, a property that reflects the abundance of charged ions able to neutralize acids, especially bicarbonate and carbonate. In warm Silurian surface waters with elevated carbon dioxide in the air, the total amount of dissolved inorganic carbon is high, but the buffering action of bicarbonate and carbonate keeps the pH of seawater slightly alkaline rather than acidic. This means that the water tends to favour the stability of calcium carbonate, particularly in shallow, well-lit regions, where photosynthesis removes carbon dioxide and pushes the balance toward carbonate ion. In such settings, organisms that build skeletons of calcium carbonate, as well as abiotic precipitation processes, find it easier to form solid carbonate minerals. At greater depths and in cooler waters, the balance shifts. Higher pressure and lower temperature favour the dissolution of calcium carbonate, and the accumulation of dissolved carbon dioxide from the decomposition of sinking organic matter raises the proportion of carbonic acid and bicarbonate relative to carbonate. There is a depth which can vary with time and location below which calcium carbonate becomes less stable and tends to dissolve faster than it accumulates. In later oceans, this horizon is known as the carbonate compensation depth. In the Silurian, a similar concept applies, though the exact depth depends on the then current carbon dioxide levels, ocean circulation, and patterns of productivity. Where deep waters are particularly rich in dissolved carbon dioxide and poor in carbonate ion, carbonate particles that fall from above may dissolve partially or completely before reaching the sea floor, limiting the accumulation of carbonate sediments in the deepest basins and favouring clay-rich and organic-rich muds instead. Oxygen is another key dissolved gas that varies with depth and location in the Silurian seas. At the surface, direct exchange with the atmosphere and the oxygen released by photosynthetic organisms maintain relatively high concentrations. Waves, currents, and wind-driven mixing draw this oxygen into the upper layers, supporting active animal life in shallow waters and on well-mixed shelves. As water parcels move away from the surface and into deeper layers, they are cut off from direct contact with the atmosphere, and their oxygen content gradually declines as microbes and animals respire consuming oxygen while decomposing organic matter. In regions where deep or intermediate waters are renewed frequently by the sinking of oxygen-rich surface water, this consumption is balanced by supply, and deep waters remain moderately oxygenated. In regions where circulation is weaker, or where a strong density stratification limits vertical exchange, oxygen consumption can outpace supply. This leads to the development of oxygen minimum zones at certain depths, and in more extreme cases to bottom waters that are hypoxic or nearly anoxic. The presence of such low oxygen layers in some Silurian basins has already been inferred from black shales and from geochemical indicators in the rock record. Chemically, the transition from oxygenated to anoxic conditions is accompanied by a change in the dominant redox processes, meaning processes that involve the transfer of electrons. In well-oxygenated waters, organic matter is oxidized mainly using oxygen-producing carbon dioxide and water. When oxygen becomes scarce, microbes turn to other oxidants available in seawater, such as nitrate manganese oxides, iron oxides, and sulfate. Of these, sulfate is abundant in marine waters because it is a major component of dissolved salts, so sulfate reduction often becomes a key pathway in anoxic sediments and waters. This process produces hydrogen sulfide, which can react with iron to form pyrite. The distribution of these redox reactions with depth and across basins strongly influences the chemistry of trace elements and nutrients. Nutrients are the dissolved forms of key elements that primary producers require to build organic matter. Among the most important are nitrogen, phosphorus, and a suite of trace metals including iron. In the Silurian, as in other times, nitrogen in the ocean exists in several forms including nitrate, nitrite, ammonium, and organic nitrogen. Nitrate is the preferred form for many planktonic organisms, but its concentration depends on the balance between processes that create it, such as the oxidation of ammonium, and processes that remove it, such as denitrification under low oxygen conditions. Phosphorus is chiefly present as phosphate, which tends to bind to particles and can be removed from seawater when those particles sink and are buried, especially in oxygenated settings. Iron and other trace metals often arrive from continental weathering via rivers or from hydrothermal sources along mid-ocean ridges, and they can be quickly scavenged by particles or precipitated in certain redox states. The overall distribution of these nutrients in Silurian seawater is shaped by three broad processes: input from land and seafloor sources, regeneration during the decomposition of sinking organic matter, and physical transport by currents and mixing. Rivers draining Silurian continents carry dissolved phosphate nitrate, or its precursors silica, and trace metals from weathered rocks into coastal seas. Weathering rates are influenced by climate uplift and the extent of exposed rock, so tectonically active mountain belts and warm wet regions can be especially important sources. At mid-ocean ridges and volcanic arcs, hydrothermal circulation leaches metals from hot basalt and deposits them into the deep ocean, adding iron, manganese, and other elements. These inputs establish the initial nutrient content of different water masses, but it is the internal cycling that largely determines how much is available in the surface layer at any given time. When phytoplankton and other primary producers in the euphotic zone take up nutrients to build new organic matter, they incorporate nitrogen, phosphorus, and trace metals into their cells. After these organisms die or are consumed, their remains sink. As they fall, bacteria and other decomposers break down the organic material, releasing dissolved nutrients back into the water in deeper layers. This regeneration concentrates nutrients below the surface mixed layer, in regions where deep or intermediate waters later rise toward the surface through upwelling. These regenerated nutrients are brought back into the light, fueling new rounds of productivity. Thus, there is a vertical loop in which nutrients are taken from surface waters, transported downward with sinking particles, and then returned to the surface by physical processes. In the Silurian Ocean, the strength and location of upwelling zones depend on wind patterns, basin geometry, and the presence of continental margins. Where winds drive surface waters away from coasts or from certain latitudes, deeper water rises to replace them. Along some Silurian continental edges and around promontories of flooded shelves, such upwelling can occur, bringing nutrient-rich water into the photic zone. These areas likely support higher primary productivity and greater organic carbon flux to depth than surrounding regions. In epicontinental seas where depths are shallow and mixing is often vigorous, nutrients regenerated in bottom waters can more easily return to the surface without requiring deep upwelling, especially during storms and seasons of enhanced mixing. The chemistry of nutrients is also tied to redox conditions. Under well-oxygenated conditions, phosphate tends to be adsorbed onto iron oxide particles in sediments, effectively removing it from the water column when those sediments are buried. Under low oxygen or anoxic conditions, iron oxides can dissolve, releasing bound phosphate back into the water. This release can locally increase nutrient levels, promoting further productivity and potentially reinforcing low oxygen conditions if additional organic matter sinks and decomposes. Similarly, denitrification in low oxygen zones removes fixed nitrogen by converting nitrate to nitrogen gas, which escapes to the atmosphere, reducing the ocean's inventory of bioavailable nitrogen. These feedbacks mean that episodes of widespread low oxygen in Silurian oceans are not just physical events, but also chemical reorganizations that adjust the nutrient balance and the pattern of primary production. Trace elements such as iron and manganese undergo their own redox-sensitive cycles. In oxygenated waters, iron is mostly present as insoluble oxides and hydroxides, which tend to form particles that settle out or become part of sediments. In low oxygen waters, iron can exist in more soluble, reduced forms, allowing it to remain in solution longer and to be transported farther before precipitating. This has implications for iron availability to phytoplankton, especially in regions where dust input from land is limited. Hydrothermal sources provide an additional supply, but their impact on surface waters depends on the pathways of deep water circulation. Over Silurian timescales, changes in the balance of these processes can alter the trace metal inventory of different basins, leaving subtle signatures in the rocks. Overall alkalinity and the ratio of calcium to magnesium in seawater influence which carbonate minerals are favoured and how easily they precipitate. Geochemical and sedimentary evidence suggests that the ratio of calcium to magnesium may differ in Silurian seawater, compared with later periods affecting whether calcite or more magnesium-rich carbonates are more common. These differences, combined with temperature and saturation state, help explain the dominance of certain carbonate textures and mineralogies in Silurian reefs and platform deposits. In restricted basins where evaporation is strong and circulation limited, concentration of salts can lead to the precipitation of calcium sulfate and eventually sodium chloride, as previously noted. The stepwise removal of these salts from solution changes the residual brine chemistry, sometimes driving dense saline waters to sink and spread along the seafloor. In this way, evaporative concentration and brine rejection can contribute to local density-driven flows that influence the distribution of both salinity and dissolved species. Through all these linked processes, the chemistry of Silurian seawater is not static. It responds on long timescales to tectonically controlled weathering and volcanic outgassing, and on shorter timescales to shifts in productivity, circulation, and redox state. Yet at any given moment within the period, the oceans present a coherent pattern: surface waters that are slightly alkaline, oxygenated, and variably enriched in nutrients depending on their history; deeper layers that carry regenerated nutrients and lower oxygen; and specific basins where stagnation or restriction leads to distinctive chemical environments. This chemical structure underlies the physical and biological patterns of the Silurian seas, providing the dissolved framework within which organisms grow, sediments form, and the signals of the period's environmental behavior are stored for future reading in the rocks. In the Silurian seas, marine ecosystems at large scale are organized along gradients of depth, distance from shore, and oxygen and nutrient availability, with different communities occupying the open ocean, the shelves, the reefs, and the deeper basins. At the foundation of these ecosystems are the primary producers in the sunlit surface layer, where light, dissolved nutrients, and appropriate temperatures allow the conversion of inorganic carbon into organic matter. Microscopic photosynthetic organisms including cyanobacteria, simple green algae, and a diverse group of organic walled microplankton, often grouped as acritarchs, float freely or remain suspended near the surface. They absorb light and dissolved nutrients and form the base of food webs across much of the ocean. Their abundance and turnover, combined with the physical structure of the water column, create a steady supply of organic particles that sink into deeper layers, linking surface production with mid-water and seafloor processes. Alongside these producers, the zooplankton component includes small, free-swimming organisms that feed on phytoplankton and on each other. Among them are early crustacean like arthropods and other small invertebrates, as well as the planktonic stages of many benthic animals. Graptolites, which construct colonial skeletons that drift in the water column, are especially notable. Their delicate structures house multiple individual zooids that filter particles from the surrounding water. Graptolite species are distributed along environmental gradients in depth and distance from shore, with some favouring outer shelf and slope waters, and others more open ocean settings. Their widespread presence and rapid evolutionary turnover make them important components of Silurian offshore ecosystems and useful markers in the rock record. Moving toward larger, more active animals, nectonic groups occupy the pelagic zone in various ways. Jawless fish or agnathons, including armoured forms such as heterostracans and anaspids, are common in many environments, especially on shelves and in nearshore waters. They possess bony head shields or scales and feed by suction and filtration, scraping, or drawing in small particles from the substrate or water column. During the Silurian, the first vertebrates with true jaws appear and diversify. Early jawed fishes include smaller canthodians, often called spiny sharks in later literature, as well as the first representatives of bony fishes and cartilaginous lineages. These new forms exploit a range of food sources, including larger prey items that were previously more accessible to arthropods and cephalopods. Their jaws and improved fins allow more precise biting and more controlled swimming, and they begin to occupy active predator and omnivore roles in the water column and near the bottom. Cephalopods remain significant elements of many Silurian marine communities. Orthoconic nautiloids with long, straight shells partitioned into chambers continue from earlier periods, though their dominance declines after the prior extinction. Coiled and curved forms also appear and expand. These animals are capable swimmers using jet propulsion and directional control to move through the water. They likely prey on smaller swimming animals, including fish and arthropods, and on larger plankton, contributing to mid and upper trophic levels in open and shelf seas. Their shells, when they sink after death, add to carbonate sediments and provide hard substrates for encrusting organisms on the seafloor. On the seafloor itself, benthic communities differ between soft substrates and hard reefal surfaces. On soft bottoms of the inner and outer shells, brachiopods, bivalves, trilobites, and echinoderms are common. Brachiopods anchor themselves to the substrate or to small hard objects using stalks, filter feeding from the water above. Bivalved mollusks occupy similar niches in some settings, lying on or shallowly buried in sediment and filtering suspended particles. Trilobites crawl and burrow across and within the sediment, grazing on organic films, detritus, or small invertebrates. Their distribution reflects environmental preferences. Some species are most abundant in shallow, well-lit environments, while others favour deeper, quieter waters on the outer shelf or slope. Crinoids, which are stemmed echinoderms, raise their feeding arms into the water column from fixed positions on the seafloor or attached to hard objects. They filter plankton and suspended particles from passing currents. In Silurian rocks, crinoidal limestones made of accumulated skeletal fragments show that in some regions these organisms form dense meadows, especially on relatively firm substrates swept by moderate currents. Other echinoderms, such as cystoids and starfish, also appear in various benthic assemblages, adding to the diversity of feeding modes and body plans. On and within the sediment, a variety of trace-making organisms continuously rework the upper layers. Burrows feeding traces and resting impressions preserve the activity of worms and small arthropods that leave only modest skeletal remains. These infaunal and epifaunal components recycle organic matter within the sediment, influence its physical properties, and mix oxygenated water into the upper centimetres of the seafloor. Their presence is important for nutrient regeneration and for the structure of microbial communities. Reefs and associated hard-bottom habitats host their own characteristic ecosystems. The framework built by tabulate corals and stromatoporoid provides a complex three-dimensional environment with crevices, cavities, and exposed surfaces. Attached to these surfaces are encrusting bryozoans, additional corals, calcareous algae, and various small suspension feeders. Within the reef matrix and in surrounding debris fields, mollusks, brachiopods, trilobites, and echinoderms find habitat and food. The open water immediately above the reef supports planktic and nectonic organisms that take advantage of the enhanced productivity and shelter available. In some Silurian regions, reefs grow as laterally extensive belts along shelf margins, creating long quasi-continuous corridors of habitat. Elsewhere, they form more isolated build-ups on local highs or within platforms. Their position is constrained by water depth clarity and energy, but wherever they occur, they concentrate biodiversity and contribute disproportionately to carbonate production. In nearshore shallow settings, including lagoons behind reefs, tidal channels and estuaries communities show adaptations to variable salinity, temperature, and sediment load. Some brachiopods and bivalves tolerate brackish conditions near river mouths. Certain trilobites and eurypterids inhabit these marginal marine zones, feeding on small invertebrates and detritus. In restricted lagoons and tidal flats, microbial mats can cover portions of the substrate, stabilizing sediments and providing a surface for grazing. Cyanobacterial mats and other microbial communities contribute to fine layering in some carbonate and siliciclastic deposits and influence the microtopography of the seafloor. Large arthropod predators, particularly eurypterids or sea scorpions, occupy a prominent place in many Silurian shallow marine ecosystems. Some eurypterid groups live as active swimmers in nearshore and shallow shelf waters using paddle-like appendages for propulsion. They prey on fish, smaller arthropods and other benthic organisms. Other eurypterids remain more closely associated with the bottom, scavenging and hunting along substrates in lagoons and marginal marine environments. Their distribution patterns suggest that they thrive especially in warm, relatively shallow waters with suitable salinity and oxygen levels. Fossil assemblages dominated by eurypterids in some formations indicate that at least locally they are major components of the fauna and can be important predators in their ecosystems. Fish communities in Silurian shelves and embayments include both jawless and jawed forms. Jawless armored fish graze and filter, while early jawed fishes introduce new feeding strategies. Some specialize in crushing or nipping, others in capturing small swimming prey. Their sizes are generally modest, but a few lineages achieve larger body sizes and begin to occupy higher trophic positions. In shelf settings, fish share space with cephalopods and eurypterids as part of a complex predator guild. The balance among these groups varies from region to region, reflecting differences in environmental conditions and in local history, but in many shallow seas, arthropods remain prominent competitors for top predator roles during much of the period. In deeper shelf and slope environments below the main photic zone, communities adjust to lower light and often reduced oxygen. Suspension feeders such as brachiopods and crinoids still occur in areas where currents deliver sufficient food, but their diversity and abundance may be lower than on shallower shelves. Deposit feeders that consume settled organic matter become more important, including certain trilobites, polycate worms and other infaunal animals. In zones where oxygen is reduced but still present, communities may be dominated by a smaller set of tolerant species. In fully anoxic bottom waters, animal life on the seafloor is absent, and microbial processes control the breakdown and preservation of organic matter. The overlying water column in such regions can show low diversity and altered plankton communities, though the details depend on local conditions and the degree of stratification. Across all these settings, food webs link primary producers to higher trophic levels through multiple pathways. Planktonic producers support zooplankton, which in turn support nectonic predators and larger benthic filter feeders. Part of the organic matter sinks out of the surface layer to feed midwater and benthic decomposer communities, while part is recycled quickly near the surface. The proportion that escapes rapid oxidation and becomes buried in sediments varies with oxygenation and sedimentation rates. In regions where burial is efficient, black shales and organic-rich mudstones record a higher flux of organic matter to the seafloor, and reduced breakdown often associated with expanded low-oxygen conditions. Recovery from the prior mass extinction shapes the structure of these ecosystems. Early in the Silurian communities often show reduced diversity and somewhat smaller average body sizes in some groups, consistent with a lingering Lilliput effect. Over time, diversity increases as surviving lineages radiate and new forms appear. Reef systems expand, jawed fishes diversify, graptolite faunas reorganize, and trilobites and brachiopods repopulate many niches. The resulting ecosystems are not identical to those of the preceding period, but represent new combinations of taxa and interactions built on the surviving foundations. This ongoing recovery and diversification unfold within the constraints of the physical and chemical setting already described: warm climate, high sea level structured water columns, and evolving patterns of nutrient and oxygen distribution. Regional variability is significant. Differences in latitude proximity to major landmasses, basin geometry and water mass structure ensure that Silurian marine ecosystems are not uniform from one ocean region to another. Some shelves favour carbonate platform communities dominated by reef builders and associated faunas. Others, closer to active margins or large river inputs, favour mixed or siliciclastic dominated assemblages with different compositions. Slope and basin communities vary with depth and redox state. However, at the scale of the entire Silurian Ocean, recurring themes appear: plankton-based food webs in the surface layers, diverse benthic communities on shelves and reefs, prominent arthropod and cephalopod predators in many shallow seas, and a growing role for jawed fishes in both near-shore and more open settings. Within this framework, marine life gradually rebuilds and reshapes itself, filling the physical and chemical spaces provided by the Silurian Earth system, and leaving an imprint in the fossil record that reveals both the stability and the dynamism of these ancient seas. On land during the Silurian, the surfaces of continents present a landscape very different from one with extensive forests and soils. The arrangement of continents described earlier means that much of Gondwana stretches across higher southern latitudes, while Laurentia Baltica and smaller blocks occupy equatorial to temperate zones. Across these land masses, the dominant features are rock-loose weathered material and networks of channels and lowlands that collect water, with only a thin and patchy cover of early plants and fungi in favoured locations. Large portions of the interiors remain bare or only sparsely colonised, especially in arid belts where rainfall is limited, and where moisture rather than light restricts the spread of terrestrial life. The starting point for these surfaces is the interaction between rock atmosphere and water. Exposed bedrock, whether composed of ancient crystalline cores, sedimentary successions or volcanic units, undergoes physical and chemical breakdown under the influence of temperature changes, wind and precipitation. Mechanical weathering processes such as thermal expansion and contraction frost action, where temperatures fall below freezing, and abrasion by wind-blown particles break larger rocks into smaller fragments. Chemical weathering processes driven by carbonic acid in rainwater and by the presence of dissolved oxygen attack minerals and alter them into clays oxides and dissolved ions. The rate and character of these processes vary with climate and with rock type. In warm, wet coastal and lowland regions, chemical weathering can be intense, leaching soluble components and leaving behind residual clays and iron oxides. In drier or colder uplands, physical disintegration dominates, producing coarse scree and thin covers of fragmented material. Because land plants with deep interconnected root systems have not yet spread widely, there is little structural reinforcement of near-surface material. This makes slopes more prone to erosion, and rainfall events can readily mobilize loose debris into gullies, channels, and alluvial fans. Streams and rivers carve networks that drain highlands toward the seas. In some areas, these networks are relatively simple, following structural controls such as fractures and bedding planes. In others, they develop more dendritic patterns where rock properties are more uniform. Along their courses, rivers pick up and transport sediments, ranging from fine silt and clay to sand and gravel. During high-flow events, they can carry coarse loads far downstream, depositing them as bars and cross-bedded channel fills. During lower flows, finer particles settle on floodplains when channels overtop their banks. Over time, this activity builds stratified accumulations of fluvial deposits, punctuated by intervals of non-deposition or erosion when channels shift or when climate reduces runoff. coastal lowlands and deltas form where channels meet rising sea level or epicontinental seas. In these areas, the energy of flowing water drops as it enters standing water bodies, and sediments are laid down in mouthbars, distributary channels, and interdistributary bays. The position of these systems changes as sea level rises or falls, as subsidence alters the relative elevation of the land and as sediment supply fluctuates. During the Silurian high sea levels mean that many river mouths are drowned, forming estuaries and fjord-like inlets in places where glacial erosion has carved deep valleys earlier. The presence of tidal currents further shapes these coastal areas, reworking deposits and producing mixed tidal and fluvial facies. On many exposed land surfaces, especially in the interiors of Gondwana and other large continents, aridity limits the development of continuous water bodies. In subtropical belts under descending limbs of atmospheric circulation cells, high evaporation and low rainfall create broad zones where streams are intermittent and where large portions of the landscape are drained by ephemeral channels that carry water only during seasonal or infrequent storms. Between these channels, extensive surfaces of weathered rock, lag gravels and sandfields develop. Without dense vegetation to trap and stabilize material, wind can mobilize fine particles, producing local dunes and loess-like deposits. Dust lifted from these dry interiors can travel offshore, contributing to atmospheric aerosols and delivering fine material to nearby seas. Even in these drier regions, microenvironments exist where moisture persists long enough to support simple terrestrial organisms. Depressions that collect water seasonally, margins of streams and lakes, and shaded rock faces where seepage occurs provide refuges. Here, early non-vascular plants such as liverwort-like forms and simple moss-like plants, along with algal films and fungi, can establish. They remain low to the ground, forming mats or small tufts rather than tall structures. These communities contribute to the formation of the first true soils in the sense of layers of weathered material, modified by biological activity, but their extent is limited and closely tied to water availability. In more humid coastal and equatorial lowlands, plant cover becomes somewhat more continuous. Evidence from spores and plant fossils indicates that small, simple land plants spread along riverbanks, floodplains, and damp surfaces. Some of these are early vascular plants possessing internal conduits for water and nutrients that allow them to grow taller and to colonize slightly drier ground than strictly non-vascular types. Their bodies are typically composed of slender branching axes without true leaves or deep roots, anchored by rhizomes or small root-like structures that penetrate only shallowly into the substrate. Even so, their presence changes local surface conditions. They trap fine sediments, reduce the speed of overland flow during rain, and create small pockets of organic rich material as their tissues grow and decay. Fungi, including filamentous forms and perhaps larger upright structures, occupy both surface and subsurface niches. They decompose organic matter and participate in weathering processes by secreting acids that attack minerals. In some Silurian deposits, large trunk-like fossils of uncertain affinity appear that may represent complex fungal or composite organisms rising several meters above the ground. Whatever their precise biological classification, they show that some terrestrial entities reach sizes much greater than the surrounding low plants. These structures stand on soils that, although still thin compared with later forest soils, have enough cohesion and organic content to support their weight. The spread of early vegetation and fungal networks affects the physical behavior of the land surface. In areas where mats and low plants cover the ground, raindrop impact is reduced, and fine particles are held in place by roots and hyphae. This diminishes the immediate erosion during storms and allows thicker, more coherent weathering profiles to develop. Over time, these profiles may grade downward from organic-rich upper layers, with accumulations of plant remains and bioturbated material into zones where minerals are altered and leached and finally into less altered parent rock. Such early soils vary widely in thickness and development depending on climate topography and duration of stability, but their appearance marks a shift from purely physical weathering surfaces to biologically modified ones. Conversely, in regions where plant and fungal cover is absent or very sparse landforms remain dominated by physical processes, steep slopes shed debris through rockfalls and landslides. Sheet wash during heavy rains removes fine particles and leaves coarser material behind. Overland flow concentrates into rills and gullies that incise rapidly into soft rocks or unconsolidated sediments. In periglacial or high-latitude zones where freeze-thaw cycles occur, seasonally patterned ground and frost-induced structures can arise as sediments heave and settle, but the lack of deep-rooted vegetation means these features are not stabilized and can be reworked repeatedly. The contrast between vegetated lowlands and largely barren highlands is therefore pronounced. Along the margins of epicontinental seas, transitional zones form where tidal flats, coastal marsh-like areas, and low terrestrial surfaces blend. In these belts, early plants can extend slightly landward from the high tide line, while marine influence remains strong seaward. Periodic flooding by storms and high tides deposits thin layers of sand and mud over nascent soils, resetting or modifying their development. In some settings, repeated alternation between exposure and flooding produces interbedded layers of rooted horizons and tidal deposits, preserving in the rock record the footprint of early terrestrial colonization along Silurian shorelines. Lakes and inland water bodies, though less abundant in the preserved record than marine environments, also contribute to the mosaic of land surfaces. Where tectonics, glacial remnants, or river damming create closed or semi-closed basins, fresh water accumulates. Around these lakes, water tables are higher and soils remain moist for longer periods. This favours more continuous plant cover and the formation of organic rich layers including early peat, like accumulations in places where plant production exceeds decay under certain conditions. However, given the limited complexity of plant communities and the often warm climate, many of these deposits may be thin or easily reworked by later events. Overall, the Silurian continents show a strong gradient from coastal and riparian zones, where biological cover is more advanced to interior uplands and arid regions where rock and loose sediment dominate. The degree of connection between these zones depends on basin geometry and climate. In some sectors, broad lowlands allow the gradual inland spread of plants and fungi over tens of kilometres from the coast and major rivers. In others, narrow coastal strips are but steep dry uplifts that remain mostly barren. In all cases, the presence of even modest terrestrial vegetation alters the flux of sediments and dissolved materials to the oceans by stabilizing some surfaces, changing runoff pathways, and introducing organic matter into rivers and estuaries. From the perspective of the period as a whole, land surfaces in the Silurian stand at an intermediate stage. They are no longer entirely lifeless rock and regolith as earlier in Earth history, but they are not yet cloaked in complex tall plant communities and thick, deeply structured soils. Instead, they offer a landscape of contrast where extensive bare or sparsely vegetated interiors coexist with wetter margins that support thin but persistent covers of early plants and fungi setting. The physical and biological conditions from which more complex terrestrial ecosystems will emerge. As the Silurian period progresses, some parts of the continents begin to host the first stable terrestrial ecosystems where interactions among plants, fungi, microbes and animals form simple but persistent food webs. These systems are most developed in areas where moisture is reliable, such as along river corridors on low coastal plains around lakes and ponds, and in depressions that collect groundwater. In these settings, early land plants with vascular tissues meaning internal conduits for water and dissolved nutrients can maintain upright growth and extend their tissues above the thin layer of still air at the ground. Their stems branch and rise to heights of perhaps several tens of centimetres to over a metre in some forms, creating low stands of vegetation rather than isolated patches. Between these emergent plants, mats of non-vascular plants, algae and fungi occupy the surface, filling gaps and binding the uppermost layer of substrate. The soils that support these communities are thin but increasingly structured. At the surface lies a horizon enriched in organic matter, composed of decaying plant tissues, fungal hyphae, microbial biomass, and fine mineral particles. Below it, chemical weathering has altered primary minerals, producing clays and oxides, and releasing ions into soil water. Root-like organs and fungal networks penetrate this zone, accelerating weathering and helping to retain moisture. These features distinguish early true soils from simple weathered mantles. Within and above this substrate, energy enters the system mostly through photosynthesis, by plants and photosynthetic microbes that intercept sunlight. The organic matter they produce feeds not only their own growth, but also organisms that consume living and dead tissues. Small arthropods begin to appear as regular inhabitants of these damp terrestrial habitats. Some of the earliest known fully terrestrial animals, such as millipede-like forms, are detritivores that feed on decaying plant material and microbial films. Their segmented bodies and exoskeletons allow them to move over and through the litter layer. As they process organic matter, they fragment it and mix it into the upper soil, enhancing decomposition and nutrient recycling. Other arthropods with closer ties to marine ancestors, including relatives of arachnids and eurypterids, may still rely on water for reproduction or spend part of their life cycles in marginal aquatic environments, but some begin to exploit resources on land more extensively, hunting or scavenging among the low vegetation and surface films. Fungi play a central role in these ecosystems as decomposers and as partners to plants. Filamentous fungi infiltrate dead plant tissues and organic rich soil horizons, breaking down complex molecules and releasing nutrients that plants can reuse. In some cases, fungi form close associations with plant axes and root-like structures, resembling later mycorrhizal relationships in which fungi assist plants in acquiring water and nutrients in exchange for organic carbon. These associations improve plant access to phosphorus and other limiting elements in the mineral substrate. In addition to these microscopic and filamentous forms, larger upright structures of uncertain affinity, often interpreted as giant fungi or composite organisms, stand as conspicuous elements in some regions. Rising meters above the surrounding low plants, they intercept light and act as reservoirs of organic matter. When they die and topple, their decaying tissues provide localized zones of high nutrient availability, encouraging denser growth of smaller plants and microbial communities in their vicinity. The biotic interactions in these early terrestrial systems form simple food chains and webs. Primary producers include vascular and non-vascular plants and photosynthetic microbes. Primary consumers include detritivorous and herbivorous arthropods that scrape, chew or suck fluids from plant surfaces and decomposing material. Secondary consumers include predatory arthropods that feed on other small invertebrates. Microbial decomposers and detritivores are present at each step, breaking down waste and dead bodies, and returning nutrients to the soil and water. The absence of large vertebrates and complex plant structures keeps these webs relatively low in vertical complexity, but they are nonetheless self-sustaining in suitable habitats. Hydrology strongly influences the distribution and stability of these ecosystems. In regions where groundwater remains near the surface or where streams provide constant moisture, plant and fungal cover can be continuous along corridors that follow valleys and lowlands. Seasonal variations in rainfall and temperature still impose stress, with some areas experiencing dry periods that temporarily reduce activity or cause partial dieback. However, where climatic conditions allow early plant communities persist from one year to the next and extend slowly over time, their spores and propagules carried by wind and water into new suitable microsites. The presence of vegetation and soil also feeds back on local microclimates. Shaded ground beneath plant stands experiences reduced temperature extremes and slower evaporation compared with bare surfaces. Organic rich soils hold water more effectively than coarse sediments, creating a more stable near-surface environment and supporting more continuous biological activity. Overlying all these local processes are the broader constraints set by geography and climate. Stable terrestrial ecosystems in the Silurian are not spread evenly across continents. They cluster where water temperature and substrate are favourable. At higher latitudes or in strongly arid interior regions, conditions remain too severe for anything more than scattered microbial and cryptic plant cover. Along equatorial and temperate coastal belts, where humid air masses and frequent rainfall are more common, vegetation stands are more extensive. Tectonic settings that produce low-relief basins with poor drainage can foster longer-lived wetland-like environments, while uplifted terrains support only transient colonization in sheltered niches. Despite their limited spatial extent, these early land ecosystems have consequences beyond their immediate area. By stabilizing soils, altering runoff patterns, and enhancing chemical weathering, they increase the flux of dissolved ions and fine particles to nearby rivers and seas, influencing nutrient supplies in coastal and epicontinental waters. Organic matter exported from land in the form of plant debris and soil particles adds to the carbon available for decomposition and burial in marginal marine settings. At the same time, the drawdown of carbon dioxide by photosynthesis on land and its partial burial as organic carbon in soils contribute along with marine processes to the long-term carbon cycle. The magnitude of these contributions during the Silurian is modest, compared with later times when terrestrial vegetation is more extensive, but they mark a shift toward a more complex coupling between the continents and the oceans. At the smallest scales in the Silurian world, processes working within grains, pores, films, and thin chemical layers shape how sediments, soils, and living communities behave. On the seafloor, grains of carbonate and siliciclastic material settle from the water column and arrange themselves into loose porous fabrics. Each grain has an irregular surface where ions dissolve and reprecipitate, where organic films adhere, and where microbial cells attach. In quiet water, fine mud particles aggregate into flocks, loose clusters held together by electrostatic forces and by sticky substances produced by microbes. These flocks settle more rapidly than individual clay particles building thin laminae on the seabed. In more energetic settings, grains roll and bounce along the bottom, colliding and abrading. Fresh surfaces exposed by abrasion are more chemically reactive, and thin coatings of iron oxides, manganese oxides, and organic matter rapidly form. Within the uppermost centimetres of sediment, steep chemical gradients develop as pore water interacts with both the overlying seawater and the buried organic matter. Oxygen diffuses from the water into pore spaces and is consumed by aerobic microbes that oxidize organic carbon. Just below where oxygen becomes scarce, other electron acceptors such as nitrate manganese oxides, iron oxides, and sulfate come into play. The boundary between oxygenated and anoxic zones can lie only millimeters below the sediment surface, depending on the balance between oxygen supply and organic matter input. Microbial communities are stratified across this thin profile. Aerobic bacteria dominate in the upper layer, followed by communities that perform denitrification, manganese and iron reduction, and finally sulfate reduction at greater depths. Each step in this sequence changes the local chemistry, producing carbon dioxide, ammonium, ferrous iron, hydrogen sulfide, and other dissolved species. Where hydrogen sulfide encounters dissolved iron pyrite starts to nucleate as tiny crystals within pores or as rhomboidal aggregates. These microscopic mineral grains later become an important component of black shales and other reduced sediments. The positions of these redox fronts shift over time as sedimentation rates change as bottom water, oxygen fluctuates, and as burrowing animals disturb the fabric. Burrows and feeding traces introduce another set of microscale structures. When small invertebrates excavate tunnels, they transport oxygenated water downward and bring reduced material upward. The walls of burrows become zones of enhanced chemical reaction, coated with iron oxyhydroxides and organic films. Microbes exploit these interfaces using the steep gradients in available substrates. In highly bioturbated sediments, this continual reworking homogenizes the upper layer, blurring primary lamination, but creating a complex network of microenvironments. In contrast, in settings where low oxygen limits animal activity, laminae remain intact, and chemical gradients are more planar and stable. These differences in microscale structure are later expressed as contrasting sedimentary fabrics in Silurian rocks. Microbial mats form cohesive surfaces in some shallow marine and marginal environments. These mats consist of layered communities of bacteria and other microorganisms that trap and bind sediment, secrete extracellular polymers, and create sharp vertical gradients in chemistry over very small distances. The upper layer often hosts photosynthetic microbes that produce oxygen during daylight, while deeper layers contain organisms that tolerate low oxygen and use alternative metabolic pathways. Over daily cycles, oxygen and pH within the mat can change significantly, affecting carbonate stability. In certain conditions, these fluctuations promote the precipitation of fine carbonate crystals within the mat, contributing to the formation of laminated microbialites and stromatolitic textures. In tidal flats and restricted lagoons, repeated exposure and flooding compress and crack these mats, and fresh sediment fills the cracks, recording the interplay between biological cohesion and physical disturbance. On land, similar microscale processes operate within early soils. Mineral grains in the weathering zone are coated with thin films of water, organic molecules and microbial cells. Fungi and bacteria produce organic acids that chelate metal ions and enhance the dissolution of feldspars and other primary minerals. As these minerals break down, they release cations such as calcium, magnesium, and potassium, which are exchanged on the surfaces of clay minerals and organic particles. Pore spaces hold water whose composition differs from that of surface runoff, enriched in dissolved ions and organic compounds. Within root zones of early vascular plants, gradients in pH redox state and nutrient concentration are especially steep. Root-like structures leak organic exudates that feed microbial communities, and fungi extend hyphae beyond the immediate root vicinity, increasing the volume of soil influenced by plant activity. These root fungal microenvironments accelerate weathering and nutrient cycling compared with bare mineral surfaces. Where soils remain saturated for extended periods near streams or in low-lying depressions, reduced conditions can develop in deeper layers, creating vertical sequences from oxidized upper horizons to more reduced lower horizons. Iron mobilized in the reduced zone can move upward or downward and precipitate where conditions change, forming mottled patterns and nodules at the millimeter to centimeter scale. Even though these soils are thin, such features indicate that microscale redox cycling is already active on land during the Silurian. Within early terrestrial ecosystems, the decomposition of plant and fungal tissues occurs largely at these small scales. Detritivorous arthropods fragment litter into smaller pieces, increasing the surface area available to microbes. Bacteria and fungi colonize these fragments, secreting enzymes that break down complex polymers. The balance between production and decomposition controls how much organic matter accumulates in soils versus how much is returned to the atmosphere and local waters as carbon dioxide and other products. At this stage, accumulation is often modest and patchy, but in sheltered, persistently moist settings, organic rich layers can reach thicknesses sufficient to influence local hydrology and stability. Across both marine and terrestrial environments, diffusion and advection of dissolved substances at small scales regulate how quickly chemical gradients relax or persist. In pore waters, molecular diffusion spreads solutes from high concentration zones to low, while advection driven by pressure differences, compaction or biological pumping can move fluids more rapidly along preferred pathways. The interplay of these mechanisms determines the residence time of nutrients, electron acceptors and metabolic products within microenvironments. For example, in compacted fine-grained muds, with low permeability, diffusion dominates, and gradients can be long-lived. In more permeable sands with active burrowing advection, mixes pore waters more thoroughly, smoothing gradients and changing reaction rates. Over the span of the Silurian period, these numerous microscale processes contribute incrementally to larger-scale patterns already described. Continuous dissolution and reprecipitation at grain surfaces modify mineralogy, and cementation strengthening some sediment layers while others remain weak. Persistent microbially mediated redox cycling influences the distribution of iron, sulfur, and trace metals in sediments and developing rocks. Small variations in organic matter burial at the centimetre scale, accumulated over broad areas and long intervals, become part of the global carbon and nutrient budgets. Soils, though thin, alter the flux of dissolved substances from land to sea, and early terrestrial ecosystems create new pathways for elements to move between atmosphere, biosphere, and lithosphere. Toward the close of the Silurian, the external appearance of Earth remains that of a warm, high, sea-level world, with broad, shallow seas, expanding reefs, converging northern continents, and a largely bare but gradually changing land surface. The internal structure of its systems, however, now includes these fine-scale interactions in sediment, soils, and biological communities. As the period transitions into the next, with further tectonic assembly and continued evolution of plants and animals, the groundwork for more complex feedbacks is already present in the layering of minerals, the organization of microbial and small animal communities, and the chemical gradients that run through grains, pores, and thin films of water across the planet.